Hello everyone, welcome to the linear elasticity course. And this video, we're gonna start the first topic or the first chapter of this course of the linear elasticity. In this chapter, we're gonna discuss the mechanics of particles and the continuum mechanics. This is like an intro chapter for this course, just to understand for you just to understand what does it mean continuum mechanics, what is the relation of the theory of classical mechanics to the mechanics of particles, and what is the concept of the classical mechanics, which is going to be the main focus of this course. And then in the next chapter, we're going to move to the linear elasticity, and we're going to discuss in detail what does it mean linear elasticity and what does it mean that we do have a linear elastic material. I'm pretty sure that you do have an idea about the linear elasticity or the linear elastic material from the material science class or even from the mechanics of material class. But through this chapter, we're gonna talk, or we're gonna focus more over the theory behind the continuum mechanics, and especially the focus is over the classical continuum mechanics. So in the beginning, what does it mean mechanics? Because I mentioned here mechanics of particles and continuum mechanics. So initially, what does it mean mechanics? Mechanics, it is the field of science. You could consider that mechanics, it is a field of science in general, if that is concerned with revealing or capturing or determining the behavior of physical bodies. Physical bodies, this would include a fluid, it would be solid material, it would be any physical object that we're already using in reality in our life, different applications. Or physical systems. So mechanics, it means that it's just to understand the behavior, how these physical system or physical bodies like solid material, fluids, or any other physical system, they are behaving under different circumstances or under different excitation. When basically these bodies or physical system are subjected to some mechanical, some electrical, magnetic, or even some thermal excitations. Since we are already mechanical guys and we are interested in this course through the linear elasticity, so our main concern that is to understand how a solid material, the focus is over solid material, what is the behavior of a solid material when it is subjected to some mechanical forces, or in some cases, how about if it is subjected into some thermal fluids. This is basically our main concern in terms of mechanical point of view. But there are, in general, we would have some material or some physical system that they already working under the excitation of electrical fields or magnetic fields. And this is what mainly the physicians or the guys who are interested with the physical phenomena or the physics of these physical phenomena of physical body, they're gonna use this electrical excitations and magnetic excitation. But for us as mechanical engineer, our main concern is to study the behavior of this material when they are subjected into mechanical forces. In some cases, how about if they already subjected into some thermal forces? So to understand and capture these mechanics or these behaviors, it means that you're already studying the mechanics, or you need mechanics for these solid material or mechanics of this fluid material. So that's why, for example, we do have the solid mechanics, we do have the fluid mechanics, which are these different fields of science. Solid mechanics, if you remember some of the undergraduate courses that you studied that already related to the solid mechanics, like for example the design of machine elements, the mechanics of material course, material science, even we were dealing with solid materials and in terms of metals and ceramic material and polymers. But also you had some courses related to the fluid mechanics. It means that we are interested in studying the behavior of the fluids when they are working in different engineering systems. So this is the meaning of mechanics in general. And again, here we are going to discuss the theory behind the continuum mechanics, also the theory behind the mechanics of particle. But our main concern is the continuum mechanics, since we are talking about the linear elasticity. But it's going to be much more easy for us to understand the continuum mechanics if we discuss first the mechanics of particles. And this is what we're going to do through this course or this chapter, is to start with discussion of the mechanics of particle. We're just going to refresh your mind with something that you had an idea about it before, but we're going to go deeply through these mechanics of particles. Then I'm gonna show you the transition from the mechanics of particles to the continuum mechanics and how the theory of the continuum mechanics has been established or developed. All right. So understanding the behavior or the mechanics. So when we said that behavior, it means that we are talking about the mechanics of these materials as a response to some external excitation is needed to design this material to serve in various engineering applications. As I mentioned, for example, in the undergraduate course, before you study before you register to the design of machine elements, there was a prerequisite for the course as mechanics of material. So you should understand the mechanics of the material first to be able to design this material for different engineering application. And this is typically what we already, what you studied in the undergraduate level. So in general, we do have two types, main types of mechanics. We do have the classical mechanics and we do have the continuum mechanics. So the quantum mechanics, I'm sorry. The quantum mechanics, it is more advanced mechanics, which the physician guys already using these things a lot. The guys who are interested with physics already using the quantum mechanics a lot. But the classical mechanics is gonna be our main focus. So we're gonna focus here through this course on the classical mechanics. Make sense? So this is a very quick introduction. What does it mean, mechanics? So again, simply mechanics, it means behavior of the material under different circumstances or under different excitation like mechanical, electrical, magnetic, or thermal excitations. All right. So how about the classical theory of mechanics? Let us just focus on the classical theory of mechanics. So as I mentioned, that our main concern through this course will be the classical mechanics. So this theory assumes two main things that you should understand. The first thing, that we assume that the material, like a solid material, and our main concern or interest through this course will be over the solid material. That we assume that this solid material is a homogeneous material. Also, it is a composition of an infinite number of particles, and each one of these particles is a mass point. So three main assumptions based on which all the classical theories of mechanics that we're already using in the engineering or the courses that you studied related in the undergraduate level, or even the courses that you already studied in the mechanical engineering related for the graduate level, all of them are built up or based on the classical theory of mechanics, right? This classical theory assumes three main points. That especially for a solid material, it assumes that we do have this solid is a homogeneous material. In addition, there is a composition of an infinite number, huge number of particles, and I'm gonna let you know what does it mean, these particles. Also, each one of these particles is a mass point. What does it mean, a mass point? Is just a point, right? So let us discuss these three assumptions of the classical theory further. So if we consider here, let us consider the particle. So what is a particle in classical mechanics? The particle, it represents the main building unit of the material. So again, mechanics is the study of the behavior of physical bodies or physical system. Forget about the physical system and let us focus on the physical bodies. These physical bodies would be fluid, or it would be, these are the two phases of material. It would be like fluid, whatever it is, gas or liquid, or it would be solid material. Let us focus over the solid material. Assume that you have a solid material. So what does it mean, particle, with respect to a solid material that we are interested in its mechanics? So the particle is the main building unit of the material. As you know, if you remember from the material science class, that the material, it is a composition of some building units. This building unit, it would be like a grain in case that we are talking about polycrystalline material. Also, if you remember from the material science class, that the polycrystalline material, this is the material that is composed of so many grains. If we're gonna look to the material microstructure, you're gonna see lots of grains already arranged together and set up together to form the material that we're already using. If we're gonna talk about all the metals, nearly almost all the metals, they are polycrystalline material. And I'm gonna give you like a typical diagram of a polycrystalline material. So in let's say that we do have a material, whatever the shape of this material. If we try to look inside it somehow, you're gonna see that this material, it is a composition of so many grains. There are lots of grains inside the material microstructure. And if you remember that these grains include, these grains like the crystal, these are the crystal, and all of these grains include some atoms inside the material. In some cases, we would have these grains that include some molecules, and the molecules, it will be like the chemical composition of more than one atom together. So we're gonna say that we do have, what I'm drawing here is just the atoms or the molecules of a single grain. Like all of this part, all of this portion is just one single grain. And if you remember from the material science class that these atoms inside the grain, they do have a certain crystallographic orientation. What does it mean? It means that these atoms already oriented or arranged have a well-defined arrangement together, all of them together, to define this grain or to define this crystal, right? But so the crystal or the grain, it is just a crystal, but it is a big crystal or a random shape of the crystal, right? Then in the next one, for example, this is another grain that the second grain, it has the same atom but with a different orientation. Like it is a very similar grain, but atoms here has an orientation that is totally different than the atoms in the next grain, and so on. So generally we're gonna say that we could say that this is the orientation of the atoms and of this grain, and you're gonna have here another orientation of the other atom of the other grain. So this is what distinguishes one grain from another grain. So this is a grain in the polycrystalline material, and this is another grain for this polycrystalline material. Make sense? Then what? Since we have two grains, it means that there should be some grain boundary between them. There should be some grain boundary. And if you remember from the material science, we're going to say that this is the grain boundary of this grain, right? So this is the green thing, this is the grain boundary. And if you remember from the material science boundary, from the material science class, okay. If you remember that the grain boundary, it has a different atomic arrangement or atomic structure that is totally different than the atomic structure of any one of these grains. So this is the typical shape or microstructure. This is known as the microstructure of this overall material and of a polycrystalline material, and this polycrystalline material contains so many grains, right? The number of grains inside the polycrystalline material, if we're gonna consider like a cube of, let's say, 1 millimeter, a cube of this polycrystalline material of 1 millimeter side, you can think how huge is the number of the grains in this 1 millimeter cube of this polycrystalline material. It is so many. So that's fine to assume that we do have a polycrystalline material with an infinite number. The number of grains, it is huge. It goes to infinity. So many grains located inside. Why? Because the size of each one of these grains, it is in the micrometer scale. You're gonna have like 22,000 micrometer grain, which is gonna be like the huge, the biggest grain ever that you would have. Like you're gonna have most of them, they already located in the micrometer. So we are talking about the 20 micrometer, 25 micrometer. This is the average grain size for many of the polycrystalline material, whatever polycrystalline ammonium, steel, whatever the material type. This is the grain. So the grain, this is the main building unit of this material. Like we are repeating inside the material microstructure these grains to form the material, and all the properties of this material are dependent on the grain itself. Like if the grain is strong, the material will be strong. If the grain is weak, the material will be weak, right? In general. So this is the classical concept of a polycrystalline material. And again, the grain for a polycrystalline material is the main building unit of this material, right? In terms of mechanics, this is in terms of material science. In terms of mechanics, the particle is the grain. if we are talking about polycrystalline material, if we are studying a solid material that is made of a polycrystalline material, in this case, the particle will be the main building unit, which will be the grain. It means that the particle in the mechanics concept will represent the grain of this polycrystalline material. Make sense? How about if we are dealing, let us consider another example. How about if we do have like a single crystal material? If you remember also from the material science class that the crystal, it is a composition of so many, it is a composition of so many atoms. But these atoms inside the crystal, which it should be, the crystal is just one single grain in case that we are talking about polycrystalline. So the word poly itself indicate multiple. So if we are talking about a polycrystalline material, it means that this material is a composition of multiple crystals. Polycrystalline, it means that it is a composition of multiple crystals, if you remember from the material science class. So in general, we do have so many atoms that they already arrange it together. They already have a specific arrangement, crystallographic orientation. All of them will define arrangement of these atoms to form a crystal. And if you remember that this crystal, there is a unit cell. If you remember the definition of the unit cell from the material science class, that we said that the unit cell, this is the representative unit of all the crystal. Like this unit cell is the shape that it should be repeated everywhere. If we repeated this unit cell everywhere, we're gonna end up with the crystal, right? Like the unit cell, this is the representative building block or building unit of the whole crystal. So we're gonna say that in case that we have a single crystal, the main building unit of the single crystal will be the unit cell. And in terms of continuum mechanics, or in terms of mechanics, this unit cell is the particle that I'm talking about. So the particle again is anything that represents the main building unit of any material, whatever it is, solid or fluid material. If we're gonna talk about fluids, basically like water, for example, so it is a composition of particles, and these particles, these are the H2O, which is the chemical composition of this water particle. So each one of these particles will be the building unit of the water or the fluid. So in this case, the particle in terms of continuum mechanics will represent this particle of the water, which is the fluid. So generally, again, the particle is the representative of the main building unit of the material. This is in terms of mechanics. Make sense? So going back again to the classical mechanics. Classical mechanics, there are three main assumptions. That we assume that any solid material is first of all homogeneous. We skip this one. And it is a composition of an infinite number of particles. And again, this particle is a representative of the main building unit. Like the case of polycrystalline material, it consists of so many grains, an infinite number of grains. So this particle will represent the grain of a polycrystalline material. Make sense? And in the classical mechanics, and this is the key point here, that each particle in the classical mechanics is a mass point. So what does it mean? It's just a point, as we discussed. So we already discussed all of these parts regarding the polycrystalline material. Now we're gonna move to the other 2 points here, which are that the particle is a mass and the material is homogeneous. Let us discuss that the material is homogeneous. So as for the second assumption of the classical mechanics, which is the homogeneity, that as we mentioned, we have three main assumptions. The first one, that the material is a composition of an infinite number of particles, and this particle is the main building unit of this material, like the grain of a polycrystalline material. What does it mean that the material is homogeneous? A homogeneous material it means that the properties of the material is the same everywhere at any point belonging to the material. And the homogeneity assumption of the classical mechanics postulates or puts a condition that the material particle is a representative of the entire material properties. As we discussed, that in the classical mechanics, that the material is a composition of an infinite number of particles, and each one of these particles these particles are the representative main building unit of the material, like the grain for a polycrystalline material. So, and this basically is consistent with the homogeneity assumption of the classical mechanics. For example, if we're gonna go back again to the polycrystalline material example. So if we're gonna look to the atomic structure of the grain, we said that the atoms inside the grain, they do have a certain crystallographic orientation, well-defined atomic arrangement. And the next grain, it has another crystallographic orientation or another arrangement of atom. It is not another arrangement, it is the same arrangement of atom, but it is oriented in a different angle, right? Like we do have one direction and we do have a different direction, opposite direction or perpendicular or any other angle. In addition, if we're gonna look to the grain itself, the grain boundary, the atoms inside the grain, they are random and they do have a totally different random distribution of atom, which is totally different than the atomic structure of the grain and so on. And all the properties of the material, they are related to how we already arranging the atoms together. If you remember from the material science class, that the metallic material, they do have their own atomic arrangement that is different somehow than the ceramic material. And that's why, and the type of bonding between atoms in metallic materials is different than the type of bonding that usually exists for ceramic material. Ceramic material mainly depend on covalent bonding, but metallic material mainly depend on metallic bond. And because of the difference in the bonding or the interaction between atoms and the arrangement of atoms, we do have totally different material properties. So all the mechanical properties that we knew about the material, they are related to the atomic structure of the material or the microstructure of the material. So given this discussion, this indicates that the properties of the grain itself, it should be different than the properties of the next grain somehow, or it would be even different than the properties of the grain boundary. The grain boundary, it has a totally different properties than the grains themselves. So what does it mean? This indicates that we're already dealing with a heterogeneous material, heterogeneous or inhomogeneity. There is no homogeneity in the material properties. That the properties at this point are different than the properties at this point is different than this point, and so on. So by nature or generally, if we're gonna talk about a material like polycrystalline material in general, its properties entirely, it is heterogeneous. There is no homogeneity. But the classical mechanics assume that the material is homogeneous. So in fact, there is no material in reality that is 100% homogeneous material. Any material, whatever it is that we are dealing with, whatever it is, solid, fluid material, even gases themselves, they do have heterogeneities. There is nothing homogeneous 100%. But the homogeneity that we're already using in the classical mechanics, it is an assumption. So that's why this is a theory that would be valid or it would be invalid in some other circumstances or in some other cases. So what about the homogeneity? The homogeneity postulates a condition that the material, that the size of the grain, it should be very infinitesimal. It means that it should be very small inside. The grain, it should be very small. And the number of the grains are huge. And these grains are very random in the material microstructure. So the overall behavior or the overall properties of the material, we can assume that the overall properties of the material are homogeneous. But if we go deeply inside, very close to the grain, we will realize that the properties of the material are in fact heterogeneous. But if we're gonna look to the material from the bigger scale, from the macroscopic scale, we're gonna see that this material is in fact almost 100% homogeneous. That is fine to assume that this material is a homogeneous, but this requires some conditions, that the size of the grain in comparison to the size of the entire material, it will be infinitesimal. It means it should be very, very small in size in comparison to the material. But as we come closer to the grain size, or decrease the material size to be very close to the grain size, we're gonna feel and we're gonna see and we will relieve and realize the heterogeneity of the material microstructure. But as we scale up and look from the bigger view, we will not see or sense the heterogeneity of the material microstructure, and in this case we can deal with the material as a homogeneous material. This is the meaning of the homogeneity assumption of the classical mechanics. So the homogeneity assumption postulates the condition first that the material particle, which is the representative of the material, it should be very small and it is representative of overall the material properties. Like the grain, one single grain is a representative of all the properties of the material, and this is basically what we consider when even from the material science class, right? But in fact, there are some heterogeneities. We disregard these heterogeneities at the larger scale, but these heterogeneities will be big deal as we come closer to the grain size or come closer to the microstructure or the grain boundary scale. Make sense? So the properties, what does it mean? The material is homogeneous. It means that the properties of the homogeneous material at any point, whatever it is representative to the whole. It means that the properties of the material are the same. We're gonna say that the properties of this are the same everywhere within the material domain. Like if you try to probe, let us assume that you have a material like this one, and if you try to measure the mechanical properties of this material at this point, or this point, like point A and point B, you will find that the properties at point A is typically like the properties of the material at point B, at point C, everywhere is the same. So we're gonna say that all the properties, this material is a homogeneous material. It has the same mechanical properties or the same properties everywhere. But in case that we do have a material that is heterogeneous material, if you try to probe or measure the mechanical properties of this material at two different points, you're gonna end up with two different properties. Like for example, the Young's modulus at point A, it will equal to the Young's modulus at point B. In this case, if they are not equal, it means that we do have heterogeneous material. But in this case, in case that the Young's modulus at point A equal to the Young's modulus at point B, equal to the Young's modulus at point C, and so on. So this indicates that we do have a homogeneous material. Make sense? So this is the homogeneity assumption of the classical mechanics. But how about if we do have a heterogeneous material? A very typical example of a heterogeneous material is the composite material. We knew, or a function graded material. Function graded material, it means that the mechanical properties of a function graded material change over space, change from one point to another point. It means that, for example, if we consider a composite material by definition, it is a heterogeneous material. The simplest way, for example, of making a composite material, like you're gonna build fibers inside matrix. If you remember from the material science class, like we do have, these are the reinforcing fibers, and we're gonna have here, this should be the matrix material, this should be the matrix, and intuitively the matrix, it should be a different material than the fiber themselves. There is no chemical composition here to end up with a composite material, but you do have two distinct materials inside that they already working together to give a new material with some properties that totally different than the matrix material properties or the fiber material properties. So if we try to probe the test or measure the mechanical properties of at this point, you're gonna find that the mechanical properties is different than this point. Like point B or point A. So if we do have a tool to probe the Young's modulus at point A, it will not be equal to the Young's modulus at point B. This indicates that we already dealing with a heterogeneous material. So how about if we do have a heterogeneous material? Can we model this one using the classical mechanics? Yes, we can. But in this case, we require some homogenization approach or homogenization method. So that's why, for example, if you have any previous experience with the micromechanics models, these are homogenization. This model depend on a homogenization approach or homogenization method to convert this heterogeneous material into an equivalent but homogeneous material. This is the homogenization concept. So in the homogeneity, for example, in case that we do have a heterogeneous material and we would like to deal with this material using the classical mechanics, we have to use a homogenization approach. We have to use a homogenization approach. Like we do have so many micromechanics, this commonly known as the micromechanics models, We do have so many micromechanical models like for example the simple roll of mixture model, and we do have the Mori-Tanaka homogenization technique. We do have so many of them that would be used for different composite material, and the objective of this homogenization approach is to convert this heterogeneous material into an equivalent homogeneous material. Once we end up with this homogeneous material, this is the equivalent homogeneous material. Once we end up with this homogenized material, the equivalent one, we can use the classical mechanics. Make sense? So again, the classical mechanics that we're already using and we're gonna use through this course, it depends on three main assumptions. These three main assumptions are that the material should be homogeneous, that the material is a composition of an infinite number of particles, and these particles should represent the main building unit of the material, like the case of the grain, like the grain of a polycrystalline material. Another point here, that the particle is a mass point, that this main building unit of the material, this particle, it should be a point. So what does it mean this? A point, in terms of geometry, a point, it means that it should be very infinitesimal, it should be very small in size. So what does it mean? It means that if we are talking about a polycrystalline material, the particle in the mechanics represent the grain, and the condition is that the grain, it should be very small in size in comparison to the overall material size. So for example, as we mentioned, we give an example of a cube of 1 millimeter size. 1 millimeter cube, it contains so many number of grains. The size of the grain in this case in comparison to the overall material size is very infinitesimal, is very small. This is the entire material, this is the material, and in this case, this little small thing, it should be the particle. In this case, very small thing, and it's just a point. Make sense? So a material particle that is a point has only one type of motion. One type of motion. What this type of motion? That it can only move with no rotation, with no deformation. A point, it can only move along X, along Y, along Z, but it cannot rotate or cannot deform. To have for any object to be deformable or can rotate, it should have a shape. There is no, the point itself has no shape. For example, if you do have a point like this one, this point can only move along X and can move along Y and can move along Z. But if we do have an object with a shape that has size and shape, so this one can move as well along X, can move along Y, can move along Z. Also it can rotate about X, right? It can rotate about Y, it can rotate about Z, it can be deformable. It means that you can change its shape. So to change the shape, it means that the material, it should have a shape. This thing, the object, it should have a shape. It should have a shape. So, but the point, this is just a point. So here in this case, there is no rotation, right? There is no deformation. But for this case, we have a shape. There is rotation, and there would be deformation. In addition, all of this in addition to the translational motion, that it can move along X, along Y, along Z. Here we have only translational motion. And this is very similar. If you remember in the dynamics class, you studied dynamics, right? If you remember in the dynamics class, the first chapters of the textbook, especially the Hibbeler textbook, for example, the author covered the mechanics and the dynamics of particles. And we were representing the particle like a point. Point, it can only move. Then we move to the rigid body motion. Rigid body, since we are talking about a body object, it should have a shape and size. So it would have translational motion and rotation, because we were studying the rigid body motion. So it was just rotation plus translational motion. There was no deformation in the dynamic class. Make sense? So since we are talking about a particle in the classical mechanics, this particle is just a point, right? So it has only one type of motion, that it can only move. Like the particle, a material particle that is a point, has only one type of motion, that it can only move with no rotation, with no deformation. Make sense? It's just a point. Therefore, the kinematical degrees of freedom, what are the degrees of freedom? These are the possible motion or the possible type of motion that any object would exhibit or any object would do. Like a point, it can only move along x, along y, along z. So we're gonna say that the point has only 3 degrees of freedom. And these 3 degrees of freedom are displacements. It means that you're going to have a displacement of this point along x, a displacement of this point along y, along z, and so on. So these just 3 degrees of freedom. So in total here we do have 3 degrees of freedom. But for example, for this case, let us assume that we do have a rigid body. For rigid body, it means that no deformation. It is not deformable. It won't gonna deform. It has only rotation plus displacements or translational motion, just it. So for the case that we do have a rigid body, it will have 6 degrees of freedom. Why? It would move along x, it would move along y, it would move along z, it would rotate along x, about x, it would rotate about y, it would rotate about z. So we do have translational motion or displacement parallel to x. We do have ux, displacement parallel to x. We do have uy, displacement parallel to y. We do have uz. In addition, we do have theta x, which is rotation about x. We do have theta y, which is rotation about y. We do have theta z, which is rotation about z. So in total, we're going to say that we do have more than 3 degrees of freedom. We do have in total 6 degrees of freedom. How about if this object is deformable, so the number of degrees of freedom will increase to 12, for example. Make sense? So the classical mechanics assumes that the particle is a point. Assume that the particle is a point. So what does it mean, a point? It means that it has only 3 translational degrees of freedom or 3 displacements. It means that the particle can only move along x, along y, along z. There is no rotation, there is no deformation. Make sense? How about if we decided to represent the particle as a volume element, as something that has a shape? It is not just a point. So what's going to happen? What do you think? In this case, we're going to have more than 3 degrees of freedom if we decided to represent the particle that form or represent the entire material properties of the classical mechanics. If we decided to change the classical mechanics, if we decided to set up new theory of mechanics, in this case, we have to adapt or modify this classical mechanics and to consider the particle that would have a shape that would rotate and move. So we can have extra degrees of freedom, and this is basically what the advanced theory of mechanics, which is related to the quantum mechanics. So that's why in the beginning we said that we do have 2 types of mechanics. We do have the classical mechanics and we do have the quantum mechanics. Quantum mechanics, it is a more advanced mechanics that consider advanced things that higher than the thing that already considered by the classical mechanics. So one of the things, for example, that the classical mechanics assume that the material is a composition of particles and all of these particles are just points. This is according to the classical mechanics. So going back again to the 3 assumptions of the classical theory. So the classical theory of mechanics, it assumes that any solid material, it is homogeneous. What does it mean, homogeneous? It means that the properties of the material at any point is the same. And this homogeneity assumption based on the condition that the material, it should be a composition of infinite number of so many number of particles, and each one of these particles, it should be a point to be representative of, and this particle is the representative building unit of the material. In case that would have a polycrystalline material, this particle would be a grain. In case that would have a crystalline, single crystal material, it would be a unit cell, it would be a molecule inside the material microstructure. It means that the particle is the representative building unit of this material. And this particle, it should be infinitesimal, very small in size. It should be a point, mass point, and the number of this particle is huge inside the material microstructure. And in this case, we are assuming that the material is homogeneous. These are the 3 main assumptions of the classical mechanics. If we decided to change any one of these assumptions, we are changing the classical mechanics. We are building like new theory. Make sense? In case that we do have, we mentioned that in case that we do have inhomogeneous material, like the case of composite material, we have to plug in between. Before we apply classical mechanics, we have to use a homogenization technique to come up with an equivalent homogeneous material. Then we can apply the classical mechanics. Classical mechanics assume that the particle is a point. A point, it has only 3 degrees of freedom, that it can move along x, along y, along z. It has no shape, it has no size to be deformable or to be rotational. It means that to rotate. But if we decided to build a more advanced mechanics, and these are the non-classical theories, these theories has been established already. We do have these advanced theories. In this case, we have to deal with this particle like a volume element, and in this case, we're gonna have extra degrees of freedom, not just 3 degrees of freedom as displacements. Make sense? Another point here, which is this one, if you remember from the vibration class or even the dynamic class, that the number of equations, if we're going to talk about the equation of motion, like we said that this is the material, and this material is a composition of so many points, so many particles. We do have a particle here, another particle, and so on. And according to the classical mechanics, all of these particles, each particle will move. You're going to see that this particle is moving in this direction with a displacement. This particle is going to move in this direction with another displacement. This one is going to move in this direction with another displacement. So we're going to end up with like some changes in the shape of the entire material because of the motion of these particles, right? So the behavior of the material itself, it depends in fact on how these particles, which are the representative of the main building unit of the material, are moving or vibrating inside the material microstructure. Make sense? So in generally, this displacement represents the motion or the vibration of the particle within the material microstructure. These are the 3 degrees of freedom. As a result, we expect that the equilibrium of the material is described by 3 equations of motion in the context of the classical mechanics. If you remember from the vibration class, that in the beginning of the class, you studied single degrees of freedom systems. What does it mean, a single degree of freedom massive spring system or vibrating system? It means that this system has single degree of freedom, just 1 degree of freedom, and to describe the motion of this system, it should be described by only 1 equation of motion. Why? Because it is single degree of freedom. And then you moved in the vibration class to the 2nd degree of freedom system, that you'd have a mechanical system or a vibration system that of 2 degrees of freedom. So we drive it 2 equations of motion to describe the motion of this vibrating system, right? So in total, the number of equations of motion that is going to describe the motion of any object, whatever it is, depends on the number of degrees of freedom that this object has. So for example, if we have an object like a point that has only 3 translational degrees of freedom, to fully describe the motion of this point, it should be fully described using 3 equations of motion, 1 equation for each one of the 3 degrees of freedom. In case that we do have an object or a particle that is deformable or rotational, it means that we're going to have extra equations of motion, more than 3 equations of motion to account for the rotation or the deformation of this particle. But in the classical mechanics, we assume that the particle is just a point. So what does it mean? It's just a point. It has 3 degrees of freedom. So that's why in the classical mechanics, the equilibrium or the dynamic equilibrium of the particle is only describable by 3 equations of motion that describe the motion of the particle, of each individual particle inside the continuum. We can find these displacements using 3 equations of motion in the classical mechanics. But if we, in other type of mechanics, we do have more than 3 because we do have more than 3 degrees of freedom. So the number of equations of motion equal to the number of the degrees of freedom that we already have for a point in the classical mechanics. So therefore, the equilibrium equation in the classical mechanics, as we are going to discuss, are only 3 equations of motion. Why? Because of the point, which is only has 3 displacements if we are talking about the 3-dimensional space. Make sense? In case that, for example, that we don't have a point, and this point or a particle belong to this material, and this particle is confined to move in 2 dimensions, so 2 equations of motions are enough. If it is confined just to move in 1 dimension, so 1 equation of motion is enough. So this, the number of equations of motion, it depends on the number of the degrees of freedom allowed to the particle that you're gonna give to the particle. In total, in terms of the classical mechanics, in the most general case, in the three-dimensional space, the particle can only move in the x, y, and z direction, just 3 displacements. So in general, we do have up to 3 equations of motion for the classical mechanics. Make sense? Again, this equation of motion relates the behavior of the entire material to the motion of the particle, and thus we can study how the motion of the grains, for example, inside a polycrystalline material causes a deformation or a change in the shape of the polycrystalline material. As I mentioned, this particle is a representative of the main building unit of the material. And assume that you have a polycrystalline material, and for some reason that the grain inside the material is going to move. That we have so many grains, and we have like some of these grains are decided to move somehow because of some external excitation. So this movement of the grains will definitely result in some changes in the shape of the material, right? So, and if you try to map this thing into the classical mechanics, these grains are the particles. So as long as the particles are moving inside the material, definitely we're gonna end up with some changes in the shape of this material. And this is the meaning of mechanics. Mechanics is to expect, is to find, is to determine the behavior, the new shape of the material up on the motion of its particle. But what makes this particle move, there should be some external excitation. Make sense? So everything is related so far, right? So again, point, it means that we have 3 degrees of freedom. Therefore, we are expecting in the classical mechanics that the equilibrium equation of any particle, of any object or any material in the classical mechanics is describable only by 3 equations of motion. So what makes, and we said that the behavior of material is related to the movement of the particle. So what makes the particle move? Is a force. The particle is a point, right? A point, it can only move parallel to x, parallel to y, parallel to z. There is no rotation, right? So the thing that would cause a displacement is a force. But if you would like to give a rotation to an object, you have to apply a couple or a moment over the object to give it rotation. So the moment is related to the rotation, but the force is related to the translational motion. This is even from the mechanics of material class or the dynamic class. Make sense? So to move a point, and this is another subject here. To move a point requires force to move a point. This makes sense, right? We knew from the physics class that the force produces a work over an object. Like if you have an object and you would like to move this object, you have to subject the object into force. Like for example, assume that we do have a box, like this case. Let me do some changes here. So again, a point, it requires a force to move a point, right? Like for example, from the physics or even the dynamic class, we knew that in case that you have a box like this one, right? So let us assume that you have this box. Let me move this one down. And if you would like to move this box, you should push it with some force, right? If we apply a certain force, it's going to move with a displacement, right? Like delta U, or just let us assume that the displacement like U. And we said that, and we knew from the physics class that the work W equals F times U, which is the force times the displacement. This is gonna give us the work that you already applying to this over this box to move it. But how about if we do have another object, and this object is just, it has like another shape or another box. Let's say that we do have another, but a little bit big box, and somehow we decided to push this box from a point here, from the tip over the ground. So it will have some kind of, depending on the pushing, if it is hard somehow, this box is going to slide a little bit with the displacement U. then it's gonna try to over the surface. It's gonna have like a little bit rotation with a certain angle here, right? The rotation all the time it is measured by how much of angle that you're gonna give to give rotation to this object. So it means that this force will produce some moment, and this moment of this force will be the force times this distance, which is L. So we're gonna say that this force, it has two effects over this box or this object, that it is like a direct force, just a force. In addition, it is a moment that equals the force times the distance. So it has like two effects. The moment is the thing that is needed to give rotation. And the direct effect, this is what give a little bit push with displacement. This gives displacement or translational motion. Here we would have only translational motion because there is no room for this box to rotate somehow, so there is no moment here. Here, no moment in this case. So in general, that to give a translational motion, you require a force. To give a moment, you require a force, but not the direct effect of the force. You need the moment because of this force. Make sense? To give a rotation for any object. In the classical mechanics, we are assuming that the particle is a point. A point, it cannot rotate. So since there is no rotation, there is no moment. Or in other words, the particle cannot support any moments. The particle can only support forces because you're gonna push it, right? So you don't have a particle in general. The mechanics of the material, it is related how these particles inside the material are going to move, right? Depending on the movement of the particle, we're gonna end up with the changes in the shape of the material, or even the material will be entirely or allegedly moved from one location to another location. This basically depends on how the particles of the material itself are moving. So what makes this particle move? A force. We have to subject these forces, these particles into some force to push them to move. But we will not apply any moments over the particle. Why? Because they are points. But for some reason, if you decided to represent or consider that these particles are volume element with a shape and size and they can rotate, so in this case, we're going to say that we require forces, we need forces plus moments to give rotation and movement to these particles, right? But in the classical mechanics, forces are only required to give rotation, to give motion to the particles, since the particles are points. Make sense? So this is like a little bit long introduction to the classical mechanics, just to try to connect the different fields. And as you can see, based on this discussion, that all the courses that you have studied in the mechanical engineering, starting from the dynamic classes, the material science, all these courses mainly were based on the classical mechanics. Were based on three main assumptions: that the material is homogeneous, the material is a composition of an infinite number of particles, and each one of these particles is just a point that can only move, and therefore in the classical mechanics we would have only three equations of motion that describe the equilibrium or the movement of the particles inside the material. Make sense? So based on this discussion, we're gonna see that the mechanics, again, the mechanics is just behavior, how the material are going to behave, right? That the mechanics of the material, all of it depend on how these particles inside the material are going to move. So per the previous discussion, it is clear that the mechanics of various continua, or continua here I mean different materials, different continuums, different bodies, solid bodies, fluid bodies, whatever they are, is related to the mechanics of the particles themselves, how these particles are moving. And even if you remember from the mechanics of material class or even the dynamics, the mechanics word itself indicates two things. Mechanics, to fully study the mechanics of objects, you have to study the kinematics plus the kinetics of the object. And very simple definition to the kinematics and the kinetics. The kinematics, that you study the motion of, or study the different degrees of freedom of an object with no care what is the reason behind moving the object. Like we study the motion of the object. For example, like in the dynamic class, you study the motion in terms of the displacement, or the displacement, velocity, and acceleration. So if you remember in the dynamic class, in the start of the class, we're covering the displacement, the velocity, and the acceleration of objects. And we didn't discuss any forces, any weight, any spring force, any frictional force, right? It means that we are interested in the kinematics. Kinematics is just to fully describe the motion of objects. So in the classical mechanics, to study the kinematics, which is a branch of the mechanics, it means that we are interested in investigating how these particles are moving. But in the study of the kinematics, we will not ask what is the reason behind moving the particle. We just study the motion. But to know the relation between the motion of the object and the forces that acting on it, this is the kinetics. So the kinetics is the relation between the forces acting on an object and how this object, because of this force, is going to move. This is the kinetics. So in general, these two main branches of mechanics, these what form the mechanics of any object. So again, mechanics of any object is to study how this object is going to behave under different circumstances, right? So based on the previous discussion, you're gonna see that the behavior of any material, whatever it is, solid material, fluid material, mainly dependent on how the particles inside the material are moving. So therefore, before we study the material itself, or the behavior of the material, it is better to understand first how these particles are moving, right? And it is better to study the mechanics of the particle themselves first, and know how these mechanics of the particle would affect the mechanics of the overall material. The overall material, the study of the overall material, this is the continuum mechanics. But the study of the particles inside the material, how they are moving, this is the mechanics of particle. So therefore, the title of this chapter is Mechanics of Particles and Continuum Mechanics. Mechanics of particle, it means that we are interested in investigating and studying how these particles are moving in relation to the forces acting on the particles inside the material, and how this mechanics would affect the mechanics of the entire material, which is the continuum mechanics. So if you study the overall behavior of material, this is continuum mechanics. If you study the movement of the particles inside the material, this is mechanics of particle, or particle mechanics. Make sense? So therefore, through this chapter, we're gonna start with after this all of this just introduction to the classical mechanics, this assumption of the classical mechanics. Now we're gonna move to the study of the mechanics of particles. Then we're gonna know how we can drive the continuum mechanics, or in relation to the from the mechanics of particles. And this is gonna be for the objective of the first part of this course. Make sense so far? So as for the first part, which is the mechanics of particles, we said that we're gonna start with the mechanics of particles, then we're gonna move to the continuum mechanics. For the mechanics of particle, we are basically, to study the mechanics of the particle, we have to discretize the material into its particles. So we're gonna see the particle. Then we are going to study the motion and the mechanics of this particle, right? This is the meaning of the mechanics of particles. So the mechanics of particle would require discretizing the material into like a colony of particles. You're gonna assume that the material is just a composition of some set of particles. Very simple. And each of these particles, it should be mass point according to the classical mechanics, because we are working based on the classical mechanics. So what are the different or the physical phenomena that we would capture or drive by inspecting the mechanics of these particles of the material? There are lots of things actually that we would study by studying or drive by studying the mechanics of particle. Like for example, and this is what the physical guys already interested with, the like the dispersions of the dispersion phonons of materials. These dispersion phonons, there is used a lot in the physics. And because of these dispersion phonons, and we're gonna discuss these phonons very quick through this part. These dispersion phonons and or the dispersive behavior of material, it is used a lot in the design of this material for sound application or the optical application. All optical applications depend on the dispersion or the dispersion of waves through the material. So, and these dispersion behaviors or phonons of the material mainly depend on how particles or atoms inside a single crystal. If we're going to talk about a single crystal, so the main building unit will be the particle or the atom itself. So it means that this particle will represent the atom. So how these atoms are moving inside the material, we to capture this dispersion phenomenon phonons, we need to study the motion of the atoms inside the material in response to an incident wave, as I'm going to discuss right now. But anyway, in general, there are so many physical phenomena that we can drive by investigating the motion of the particle inside the material. You would sense this importance of the study of the mechanics of particle from the mechanical point of view for mechanical engineering, because we are interested in seeing how the material entirely is moving. So to study the entire behavior of the material or the behavior of the entire material, this is continuum mechanics. And in this case, you don't care about the motion of the particle. It makes sense? But the guys of physics, they are interested in the dispersion phonons. So to study the dispersion phonon, they have to see what's going on inside the material and how these particles inside the material are moving. But you should understand that the two aspects, the two types of mechanics are related. Whatever it is, mechanics of particle or the mechanics of the continuum, they are strictly related together. And you can drive this one from this one or this one from this one. It means that you can start from the continuum mechanics, then you can break down into or do discretization. If we did discretization of a continuum mechanics, we're gonna end up with mechanics of particle. The same thing, if we did like generalization of mechanics of particle or the particle mechanics, we're gonna end up with a continuum mechanics. It means that we can drive this one from the other one, right? So it is just different aspects how we gonna look to the material. Here in this part, let us do like the physics guys. Let us do, or we're gonna go over what the guys of physics already doing in their study of the material. They look inside the material and they are interested in the motion of these particles inside the material. And this is what we're going to do. Make sense? So for this part, we are going to discuss first two simple examples, which is very simple and it's going to be very, very familiar. You're going to be very familiar with these two examples from the vibration class, which are we're going to study two simple models of discrete particles, of discrete system of particles. Discrete system, it means that you have certain number of particles and it is discrete. It means that you can count how many particles already located or exist or you already studying. But in case that this number of particles is huge and we are interested in their motion, so we are moving to the continuum mechanics. And this is what we're going to do next, right? But in the beginning, let us consider that we have a discrete system of particles, and we're going to consider two simple examples, one of the monoatomic lattice and the second one for diatomic lattice. As you can see, monoatomic lattice, diatomic lattice, this is related to the material science or the physics, kind of, right? So then this is what we're going to do first. Then we're going to move to a more general concept of mechanics of discrete system of particle, like we're going to do generalization of the three-dimensional space. Like in these two examples, in the monoatomic lattice and the diatomic lattice, we're going to consider that we're going to work like in one-dimensional case. Then we're going to move to the three-dimensional case to end up with a general model of the discrete system of particle. Then we're gonna use this model and to drive the continuum mechanics that we are going also to discuss. Make sense? And something that I have to mention here, that the main focus of this course is continuum mechanics. We are mechanical guys. All the courses that you studied in the undergraduate level or even the graduate level, they are related to the continuum mechanics. And the linear elasticity, it is related to the continuum mechanics. Even some universities, when they offer this course, they give it a name as continuum mechanics, which should be very similar course. So our main concern is the continuum mechanics based on the classical mechanics through this course. But as I said, to understand this mechanics, it is better to go through the mechanics of particle, and this is what I'm going to represent in this part. Make sense? Let us start with the monoatomic lattice. Monoatomic lattice, it is a very simple mass spring system of single degree of freedom mass spring system that we studied in the vibration class. So it is very similar. For example, a typical shape of a monoatomic lattice model that we're gonna have one atom. Okay, let us move this one here. Okay, like we're gonna have one single atom. In this case, we're gonna have one atom, and there is another atom, and then another atom, and so on, keep going. This atom, in general, in terms of mechanics, each one of these atom or each one of these circle indicate a particle. Each one of these indicate a particle in terms of the mechanics. And as we said, this particle is the representation is a representative of the main building unit of the material. So if we are dealing with a unit cell of a crystal, and this is what the physics guys are already doing, that they consider a crystal, and this crystal is a composition of atoms. So they're gonna make a unit cell, which is the representative building unit of the crystal itself, or they're gonna make a unit cell, and this unit cell has so many atoms. So assume that we have a unit cell of the crystal, and these are the atoms of the crystal. So in terms of mechanics, these atoms are the particles. This is one model. Another model, for example, how about of all of this material, assume that this is the entire material. Of all of this material is a polycrystalline material. So the main building unit of this material are the grains. It means that there is one grain, there is another grain, another grain, another grain, and assume that all of these grains are arranged in a single chain, like in a single row in this case. Make sense? Another model, for example, how about if we are dealing with a special type of crystalline material of a single crystal that is molecular, known as molecular crystal. Molecular crystal, it contains molecules, not atoms. There is definitely some atoms, but these atoms are different and connected together to form a molecule. So we're gonna say that this is a molecular crystal. The entire material is a molecular crystal, and each one of these circles indicate what? Indicate a molecule. And in this case, according to the mechanics, each one of these particles represent a molecule. So whatever the material is, let us assume that we do have multiple particles, a set of particles already arranged over a line, horizontal line. And there should be some interaction between this particle and the neighbor particle, the next one. And there is an interaction between this particle and the next particle, and there is another interaction between this particle and the next one, and so on, and keep going. So what is this type of interaction? This interaction, it would be any form of interaction. We do have so many forms of interaction that would be generating between objects. We have gravitational force that depend on the difference between the masses of two objects. For example, if we do have like one very big object with very huge big mass, and there is a very small object with very small mass, and they are close to each other, there is a gravitational force that is going to show up, which is known as the Newtonian gravitational force. And this is what makes us already moving or sticking to the ground, to the earth. If you compare our human being mass to the mass of the earth, it is too tiny, it is too small, so that's why there is a gravitational force. And this is the commonly known, you studied this type of force in the physics class in the past, right? So it means that any two objects, there are some interactions between them. It would be gravitational force, it would be any other type of forces, whatever it is. In case, for example, if we're gonna talk about atoms, there is interatomic forces. The easiest way to understand this type of force is to understand it through an interatomic forces. Like if we assume that this is an atom with mass m, and there is another atom here. This is atom, and there is another atom, atom. All of these atoms are identical of the same mass, right? So there should be some bonding between this atom or some interatomic interactions between these atoms. And this is what you studied in the material science class. In the material science class, there was like atoms, and there should be some interactions between these atoms. This interaction is known as the potential energy between the two atoms. Then from this energy, we can convert it into some kind of forces, some like interaction between this atom. So generally, in terms of mechanics, each one of these is just particle. This is particle or atom, which would be like an atom, right? So all of these are different particles, and so on. Make sense? And there should be some interaction between them. We can, in terms of mechanical things, we can represent this interaction like a spring. Like a spring with a spring constant or a spring stiffness K. So K here stands for the spring constant or the spring. This is the spring constant, which is K, or the spring stiffness, right? And let us assume that we have all of these atoms or particles. They are confined to move along the x direction, in just one direction. There is no possibility of any one of these atoms to move in the y direction or the z direction. It is only confined to move in one direction, unidirectional lattice or unidirectional motion of these particles. That all of these particles are going to move in the x direction with a displacement, let's say like u. So for example, if we pick this atom, let us assume that this atom is atom number n, because we have so many atoms. So let us give some numbers to this atom. Like this is atom n, this should be like atom n plus 1, and this is the atom n plus 2, and so on. Like this is the atom n plus 3, and this one it should be n negative 1, n negative 2, and n negative 3, that located into this lattice. So this is this simple model of this masses and spring. This is like the vibration class, right? Like we have mass spring system, right? So these masses and this mass spring system is a representative of a commonly known as monoatomic lattice, which you can deal with these particles or these small things like atoms or particles according to the classical mechanics. In the classical mechanics, each one of these particles is a point. So a point, it can only move. There is no rotation, there is no deformation for all of these small masses. So it can only move, it would move along x, y, and z. We said that it is only confined to move along x. So here we're going to have the displacement of this mass m will be un plus 3. It means that this is the displacement for just this mass. This is the displacement just for this mass is going to be un plus 3. How about the displacement of this mass? This one will move with n plus n2. This indicates that the displacement of this atom or this particle, it should be different than the displacement of this particle or this mass or this atom. The same thing here. This one is going to move with another displacement as un plus 1. This one it will move with un, but this one is going to move with a displacement like un negative 1. This one is going to move with a displacement like un negative 2, and so on, and keep going, un negative 3, and so on. So that's why we do have so many degrees of freedom, because we do have so many different displacements, and all of these displacements are independent. So if we decided to write the equations of motion of all the atoms, we're gonna end up with so many number of equations, because we do have so many degrees of freedom. Each atom represents, it has its own displacement, so we do have so many number of degrees of freedom. Make sense? But how about if we are interested in investigating the motion of just one atom, like atom n? Let us pick the atom in the middle here, which is n. Just choose this atom here, atom n, and let us study or drive the equation of motion of just this atom. So we do have here two springs. One spring is K, the second one is K, and it is in connection with other two atoms here, like N plus 1 and N negative 1, right? That this one is moving with a displacement N negative 1, this one is moving with a displacement N plus 1. So if we decided to draw the free body diagram from the dynamics class, assume that you do have a mass M in this way, and it is connected, so we're going to consider just this simple case, like we do have another mass, which is this one, and this is the mass here, M, but this is the N negative 1, this is the N plus 1, and this is the N mass. This one is moving with UN, but this one is moving in the same direction with N negative plus 1, and this one is moving with N negative 1. According to the dynamics class, if you remember that to the free body diagram for this mass, just focus on the mass in the middle. So we're going to have the mass M. We're going to have this mass M, right? And since we do have a displacement, there is a spring stiffness here K and another spring stiffness K. There should be some spring forces. There should be one spring force for this one, and there is another spring force for this one, right? The spring force, this depends on which displacement is bigger. The direction of the force depends on which one is bigger, which one is the smaller one. If you remember from the vibration class, you can assume any displacement is bigger than the other. For example, I can assume that UN is bigger than UN plus 1, or you can assume UN plus 1 is bigger than UN, it's up to you. For example, if I assume that UN is bigger than UN plus 1, it means that the push, that this mass pushes the spring, and the spring is going to be compressed, so the spring, it should be reject this motion, it should be pushing in the opposite direction, and in this case the spring force will be K times UN negative UN plus 1. Make sense? This is going to be the spring force that generated within this spring, assuming that UN is bigger than UN plus 1, because these two displacements are in the same. So if the same direction, if UN is equal to the UN plus 1, this spring will not be compressed. But if UN is bigger, it will be compressed by the difference between the two displacements. The same thing apply here. Let us assume that UN is bigger. So if UN is bigger, this spring will be stretched, so the direction of the spring force will be opposite in this direction, and it's going to be the K times the bigger value, which is UN negative 1. Make sense? You should keep in mind that these are two different displacements, UN plus 1. For example, if to reset to the vibration class, if we set this UN plus negative 1 is 0 and UN plus 1 is 0, you're just gonna end up with a single degree of freedom system. This is a single degree of freedom system because you already have here this UN, this is the only degree of freedom that we have for this mass, and there is an inertia force that is going to generate because of the motion in the same direction of motion is the mu double dot, which is UN double dot. This is the inertia force due to motion. This is the mass times the acceleration. U double dot, this is the acceleration of this mass. Make sense? So if I ask you to apply Newton's law that the sum of forces parallel to x, it should be 0 from the dynamics or the vibration course. So we're going to say that the sum of forces along the x direction, it should equal to the free body diagram, or it should equal to, according to the Newton's law, it should equal to the mass times the acceleration, right? The mass times the acceleration, which it should be the mass times the u double dot. This should be the u double dot, UN double dot. Make sense? And how many forces do we have in this free body diagram? We have two forces. Both of them are negative because they are directed in the opposite to the direction of motion. So it means that we're going to have on the left side negative K UN negative UN negative 1 and negative K times UN negative UN plus 1. This should equal to the mass UN double dot. This is going to give us the equation of motion that describe the motion of this just one mass. So as you can see, this mass, it has only 1 degree of freedom that it can move along x direction. I confined its motion to move along x direction. But how about for some reason, if this mass can move in the x and y and z direction, so we should have three equations. But here, since we are confining it just to move in one direction, we do have only one displacement for this mass, and this displacement can be obtained in relation to the other displacements of the neighbor atoms, the other two atoms next to it, which are these two atoms. This is the equation of motion. This is the equation of motion, which is just one equation of motion. This indicates that we do have single degree of freedom system. Make sense? And this is basically the fundamental dynamical equation of a monoatomic lattice, how we can drive. So this monoatomic lattice, it means that we are assuming that we do have a unit cell, or you do have a material that consists of so many particles, but these particles are arranged in one line, and all of these particles are confined to move in one direction, which is the x direction. This type of model is known as the monoatomic, commonly known as the monoatomic lattice, and it is used a lot in the physics because as we mentioned, here we are interested in investigating the motion of the particles inside the material. Make sense? So this is the equation of motion. From this equation, we can study lots of things. This is like a vibration. So we can study the natural frequency of the vibration of this atom N. How the frequency of the vibration of this atom inside the material in case that we subject this material into some wave. Like if we give disturbance to this material, what do you think of this atom? This atom will start to vibrate, right? If you push this material with a force, this atom will move, right? So as you can see, for example, here in this model, we assume that there is no external forces acting over this mass. So that's why this is free vibrating system. There is no external force. But for some reason, if there is an external force F here, F of t, that acting on this mass, so you're gonna find here there is a term of like plus F of t as an external force acting on this vibrating system. Typically like what we did before in the vibration class. Make sense? Now we solved this equation, or we drive this equation. So how about if we are interested in finding the solution or just solving this differential equation, just ODE or the differential equation, and we have to solve it for the displacement UN, kind of. And to do so, we're gonna consider the case that this lattice is subjected to some wave, like external wave. This is one of the things. And like there is an external wave already incident to this lattice. So this wave will produce some vibration over all of these atoms, making these atoms vibrating in the horizontal direction. Keep in mind that we're already confining the motion of all of these atoms to move, or particles to move either along the x direction. It means that if we choose the atom or the particle M, it's going to vibrate over the horizontal direction in this way. So if we consider that there is an incident wave like this one that already acting over this lattice, so what will be the vibration? Let us study the vibration of the atom M, which is typically going to be the same thing that you used to do for the vibration class. So this is the equation of motion that we derived in case we added this part, in case that we have there is external force, but in case that there is no external force, this F of t will be removed or eliminated. So this is going to give us the same equation. This is still the same equation that we got, which is mu n double dot, where un, this is the displacement of the atom or the particle n, and plus 2k, which k the stiffness or the spring constant, and un, this is the displacement of the same atom or the particle, but this is these are the displacements of the other neighbor atoms, which are the un plus 1 and un negative 1, as we explained here. So, and to drive the solution of this equation, of equation 1, we should have like a trial solution. This is one of the things, and this is what we used to do in the vibration class. Like we basically assume trial function. This trial function it should be the wave that already acting over this lattice. Like if we consider that there is an incident wave, and because of this incident wave, this atom, it should be vibrating. in a certain way. And if we try to investigate this wave will have a wavelength and a certain incident frequency, and we are interested in the vibration that it will be produced because of an incident wave with a certain wavelength. So you could consider that generally we can, based on the Fourier-Bloch expansion method, this is like a trial solution of the displacement field that we which is un, or even un-1 or un+1. Basically, in the lattice mechanics, we are assuming this trial function. Normally, we are assuming this expansion like a trial function, but we used to assume a similar one in the vibration class. This is in case that we do have this atom is fixed here and this atom is fixed. So you're going to end up with a single degree of freedom. So what does it mean in this case? We're going to have this term will be 0, this term will be 0. So we're going to end up with a very simple equation of this un will be 0. It means that all of these terms will be eliminated. So we're going to end up with an ODE, and the trial function that we used to assume for in the vibration class, if you remember, it was like the UEI omega t, where omega, this should be the natural frequency of the vibrating atom, or the frequency or the speed of the vibration, which should be related to the speed of the vibration of the atom. In addition, this is the square root of 1 because we are assuming like a complex trial function. Then we're gonna plug this trial function into this equation to end up with a solution where this should be the magnitude of the vibration of this atom. So we're gonna do the same, but here in this case, we do have the other neighbor atoms are vibrating. So basically in such a case, we are assuming this trial function that depend on the Fourier-Bloch expansion theory. So this is normally what we assume for the trial function, this one, which is un, which is the displacement of atom n. It should be the u uppercase n. This should be the magnitude. So this one is the magnitude, and this is the square root of -1, which is the imaginary indicator. In addition to n, this n stands for the number of the atom itself. We are talking about atom number n. So this is the n atom number n. If you are interested, for example, in the displacement of the atom n -1, this should be the un -1, but the exponential term will have the I n will be n -1 q times this should be negative omega t. So it means that we're just gonna replace the n to be n -1 in case that we are seeking the displacement of another atom, like the atom n -1. For example, for +1, it's gonna be un +1 expansion, the exponential of the I n +1 q negative omega t, and so on. But since we are interested in un, so this should be the expansion for the un, where the un is the magnitude of the displacement of the displacement field, which is un. And if you remember in the previous video, we discussed the fields and the vector and tensor analysis, and we said that the field, it should be a function. What does it mean, a function? A function of something, of a variable like this space, like x. So in general, this u, it should be a displacement field, like it should change from one atom to the other atom, or from one point to another point, from one location to another location. So it should be a function of the space or the x in general. But anyway, this should be the magnitude of the displacement, and omega, this should be the natural frequency or the frequency of the atom vibration. What is q? Q is commonly known as the wave number, and this wave number, it can be related to the wavelength of the incident wave. We are subjecting this lattice into wave, so this wave will have a wavelength, and the wavelength, it should be this distance, for example, for any incident wave. So this should be the wavelength. This wavelength can be related to the q, which is the commonly known as the wave number. It is 2 pi over lambda. Make sense? So it is just something related to the wave science that you should have a previous experience before about these things in the physics class. somehow. But anyway, this is like, assume that this is a trial function for the displacement of the atom n. If you are interested in the displacement of another atom, so we're just gonna get rid of the n and replace with either n-1, n+1, it depends, as already given here. But we're still having the omega, where omega refers to the natural frequency of the vibration, or in other words, this should be the natural frequency or the frequency of the incident wave. How this wave is going to spread or pass through the lattice. If in case that we're already pushing or acting or subjecting this lattice into some wave with a wavelength lambda, which will be related to the wave number q, how much is the frequency of the vibration of the atom inside the lattice up on the these incident waves. Okay, so this is if we consider this one from the physics point of view. If we consider it from the vibration point of view, we're gonna deal with this one as a trial solution of this equation, and our objective is just to plug this trial solution here into equation 1 to end up with the displacement un, or the vibration of the atom n, and this is what we're gonna do. So I'm gonna do the demonstration here. This is gonna be the final equation or expression of the frequency of the atom, but I'm going to drive this one here. I'm gonna show you how we can do how we can drive this term as we did many times before in the physics and the vibration class. So for this case, as we agreed that what we're gonna do basically, we're just gonna plug this equation into equation 1. So I'm gonna do a little bit change to this formula to make it much more simple. We can assume that un equals, let me just choose this one. Let us assume that un equals u uppercase n, which is the magnitude. The exponential term, I'm gonna split it into two parts, like I and q. This should be divided or times e negative I omega t. Agree? Just I have split this exponential term into two parts, like e let me use the same expression for both. So this is gonna be like the exponential of I n q times the ei negative I omega t. So what I've did here, I split this exponential term, and let us assume that this term equals q. So we're gonna end up with un q but power n, q power n, okay, and ei negative I omega t. And from here, we're gonna end up that q, it should equal to the eiq. So for example, if we do have q power n, it should be the eiq all, it should be power n. It means that it should be the I n q, which is this same term. Make sense? In case that, for example, we do have q negative 1, it should be e negative iq, and so on. So it is just the exponent of the q, right? And then let us plug this formula into equation 1. So the first term, it is u double dot. U double dot, it means that we are going with t. This here stands for the time. So we're gonna do time derivative of this expression twice. This is gonna give us at the end negative omega m. If you try to do it, will be this term will be m. There is negative omega square, and this should be times the un qn, which is this one, ei negative I omega t. This is gonna be the first term. I've plugged the un here. Then plus 2k un is gonna be the same. So it's gonna be plus 2k u uppercase n qn negative I omega t. And then this term will be negative k, and we do have un negative 1. To have un negative 1, it means that we're gonna have the un negative 1, but this term will be, for this term here, we're gonna end up with, all right, so it seems that I've did here something wrong in this expression. If we are interested in the displacement of the atom n negative 1, this should be the same magnitude of the atom n, but we are referring to this atom n, but there should be a shift or a difference in the wave like one step before or after, depending whatever it is, n-1 or n+1 for the wavelength. So this, it means that this term, if we are interested in the displacement of the atom before the atom n, which is n-1, it means that we still gonna have the same amplitude, because this should be the amplitude of the incident wave with respect to the atom n that is located at the atom n, location n, but we're gonna have a different wavelength that will be shifted back with -1 or passed by -+1 in case that would have un +1. Make sense? So it means that we still have the same amplitude but different wavelength will be shifted here. So going back again, so we already finished this term, then we're gonna have -k, then these two terms. So if we try to work on these two terms, so we're gonna have the -k as a common factor. The first term is un-1. So un-1, we're gonna have the un, u uppercase n. The exponential term will be n-1. So we're gonna replace this one, this q, and instead of having q power n, it will be q power n-1. So it will be q power n-1, and we still have the -I omega t. This is for this one is the un-1. This is the un-1 plus the second term is the n+1. So it will be un q n+1 e -I omega t. Make sense? Where this one it will be the un+1 equals 0, because we just finished all of these terms. We don't have any external force here, which is this f of t, because we just consider the lattice that is subjected to the incident wave as given above. Then what we're gonna do next, basically, as you can see, there are some common factors that can be collected here. For example, that is fine to cancel this term with this term, can be cancelled. Also, this term can be cancelled. This one can be cancelled, because the right hand side is, anyway, it is 0, right? Then we can consider Qn as a common factor. If we decided to take a Qn as a q power n as a common factor, we're gonna end up here. This one, it should be q power -1, and this will be q power +1, right? Because you just dividing all the equation over Qn. So we're gonna end up here with this new form of this equation as -m omega square. Let me use another pen. -m omega square. Also, we can get rid of the un, the un, the un, the un. Also, there is a common factor, so we can remove this amplitude. So we're just gonna have here like Qn. I'm just gonna write the equation again in terms of Q plus the 2k Qn, q bar n, and we do have here -k times the Qn -1 plus the q plus 1, n plus 1 equals 0. Make sense? So if I ask you to get rid of or divide all of this equation by Qn, so we're gonna end up with -m omega square plus 2k, right? We are dividing by q power n, -k. This is gonna give us just -1 here plus q +1 here equals 0. Make sense? Now let us work on this in this term, in this q plus 1 and this term, how much it is. So for q -1 plus q plus 1, if you remember, how much is q -1? Q -1, it should be e -iq, or q generally it is e power iq. So if it is -1, it should be -I. If it is +1, it should be +I, right? So we're gonna have here like e -iq plus eiq. If you remember from the trigonometric, this exponential term, this iq, this complex exponential term can be expanded into cosine and sine. So for example, the negative power -iq can be expanded into the cosine of the cosine of q. The cosine of the q, it could be the cosine q plus I sine, it should be negative. It should be the negative of, because there is a negative here, sine q This is the first term, plus the second term will be the cosine of q plus the I sine q, right? So as you can see that these two terms will be cancelled, so we're going to end up with just 2 cosine q, and this is the q negative 1 plus q1. This is going to give us 2 cosine q. What is q again? This is the wave number, which is the 2 pi over lambda, which is related to the wavelength of the incident wave. So if we substitute with this term here, we're going to end up with this equation that negative m omega square plus 2k negative 2k cosine q equals 0. Make sense? So we're going to end up with a very simple equation. This equation, we used to give it a name in the vibration class as the characteristic equation. This is the equation that describes the eigenvalue equation that commonly known as the characteristic equation of the vibration, or relates the, for this case, for the wave application, it relates the wavelength or the wave number to the frequency at the atom number n. Make sense? Then simply we can, if we assumed here, let us divide this equation by m, all of it by m. So we're going to end up, or negative n, just divide by negative m, negative m, negative m, and negative m. If we did the calculation, we're going to end up with omega square. This one going to give us negative 2k over m, right? And we're going to have positive 2k over m cosine the q equals 0, right? And now let us assume that omega 0 square, it should be the k over m. Because if you remember from the vibration class that the natural frequency should be the square root of k over m. So the square of the frequency, it should be the stiffness of the spring divided by the mass for a mass spring system. So let us just give a number or a value for k over m as omega 0 square. What is this omega 0 square? Is going to be like the characteristic natural frequency of the system. This is the natural frequency of the vibrating system itself. But this omega, it should be the incident wave. This is the forcing frequency. If you remember in the vibration class, there was a natural frequency of the vibrating system itself. Like it vibrates by itself, which it should be this value. And there is the forcing frequency in relation to the wavelength of the incident wave. So depending on the frequency and the wavelength of the incident wave, for example, if you send a wave with a certain wavelength, it's going to pass through the lattice with a certain frequency omega. Or if you send a wave with a certain frequency, the wavelength of this wave through the lattice will be dependent on the natural frequency or the frequency by which you're already sending the wave. So this equation is known as the dispersion equation. This equation, it has a different name that we're going to call this one as the dispersion relation. What is the dispersion relation? This equation describes how the wave is going to propagate, or it can be dispersed by the lattice of, it means that you're going to send an incident wave, how this wave is going to propagate through the lattice. What is the speed? What is the wavelength of this wave inside the lattice? This can be described through this equation, which is known as the dispersion relation. And that's why in the physics class, or the guys who are interested with the physics of these lattices, they are interested to investigate the vibration or the responsive behavior of these atoms or these particles to an incident wave through this equation. It makes sense? So if we plugged here omega 0, we're going to end up with this equation, which is omega square negative 2 omega 0 square plus 2 omega 0 square, the cosine of q, we can equal 0. We can do further simplification to this equation by considering the omega 0 here like a common factor. So we're going to have the omega square. We can move all of these parts because we are interested in finding omega in terms of the q. So equals, if we move this one, we're going to have the omega 0 square times the 2 negative 2 cosine q, and this is what gives us the dispersion relation as already written in equation 3. All right. If we just take the square root of this one, we're gonna end up with the natural frequency. So this equation here, it relates the frequency. This is not the natural frequency, this is the frequency of an incident wave. How this is the speed. This frequency is related to the speed of the propagation of the wave through the lattice. Up on that depends basically on the wavelength, which is already located inside Q, which is the wave number. So this equation relates the frequency of the wave to the wave number of the same wave in terms of omega n, which is the natural frequency of the system. So omega n, it is a material property. Omega n, this natural frequency, it is a material property, which is the square root of k over m. What is k? This should be the spring constant here of this lattice. And what is m? This is the mass of the lattice itself. So for this lattice, the thing that fixed with this lattice are the stiffness and the mass. This omega 0, this is a natural frequency of the system. It is fixed. But the thing that would change in this equation 3, in the equation 3 down, it would be omega or q, which are that depend on the external excitation, that depend on the external force. This like the forcing frequencies or the forcing wavelengths of the incident wave, kind of. Make sense? So we end up with this equation. This equation is commonly known as the dispersion relation. In physics, the dispersion here describes the dispersion of an incident wave by a medium, like a material. Like assume that this lattice is a material and you already subjecting this lattice into a wave. So how this wave is going to be dispersed by this material, or in other words, how this wave is going to propagate through the material. Dispersion, it means that somehow you can understand dispersion like kind of distributing the wave, or kind of slowing down the wave, or changing the speed of the wave through the material. This is kind of the meaning of dispersion. So in case that the wave, for example, is propagating in air, it can be easily go through the air. But if the same wave tries to propagate through a solid material, it will be hard for it. It means that the frequency should be lower in case that we do have a solid material. And this makes sense. For example, a solid material, it has a stiffness that is much way higher than the air, for example, or a liquid material. So as we're increasing this term, this omega 0 will increase. This indicates that the natural frequency of the wave is going to increase so much up on the increase of omega 0. Increasing the natural frequency, it means that the wave is vibrating in place. It means that it is hard for the wave to go through the material itself. That's why you already sending a wave with a certain wavelength, but it is hard for this wavelength or wave to go through the material. So it will go through the material, but there is like something slowed down, not slowed down, object the motion of the wave or the propagation of the wave. So that's why instead of spreading over a wide wavelength, it will spread over a short wavelength, making the frequency very high. Because the frequency, if you vibrate, this is a very high frequency, but this is a very slow frequency. Okay, this is in terms of the wave propagation. We won't gonna go deeply through all of these details, but basically this is one of the phenomena. For example, all the design of these lattices and crystal material for sound application or even optical application depend on these calculations. So the key point here that I'd like to demonstrate is that there are some phenomena that we can extract by studying the vibration or the motion of the particles inside the material, right? This will not be the main concern of this course as a linear elasticity, but as I said, it is better to understand continuum mechanics or linear elasticity from the mechanics of particles point of view. So that's why I'm presenting this part first. Make sense? Then, now let us go back here. If we try to draw this equation, this omega versus the q, which is the wave number. This q basically changes from negative infinity up to positive infinity, or it is commonly that it would change from negative pi to positive pi. So if we try, I'm gonna give you like a typical diagram of this dispersion relation. So now let us draw this equation here. So to draw the equation, let us do some simple calculations of the limits. So we're gonna draw this equation from Q equals 0 or negative pi up to pi. So, but this means that we have to consider the case that q equals 0. So if we set up the coordinates in this case, like assume that this is the y direction that should be for omega, and this x direction or this x coordinate, this should stand for the q, right? That this should be the q direction, and this should be the omega vector. So and the equation again, it is omega equals plus or minus omega 0 the square root of 2 times 1 negative cosine q, right? So for the case that q equals 0, what should be omega? You're gonna find that omega will be 0, right? Because cosine 0 is just 1, so 1 negative 1 gives 0, so this everything will be 0. So the first point that we have here, that when q equals 0, this is q equals 0 here, q equals 0, then we're gonna calculate at q equals pi, the same thing is gonna be at negative pi, right? So, and for q equals 0, we're gonna end up with that omega will be 0, so this is gonna give us the first point. Then let us find the value of the omega when q equals pi or negative pi. If you plug pi or negative pi, this term will be negative 1, so negative 1 times negative, this gives positive, so this term will be positive 2 times 2 will be 4, so the square root of 4 gives 2, so we're gonna end up that omega will be plus or minus, forget about the plus or minus for now, so omega will be the square root of 4, which it should be 2 omega 0. So it means that when q equals pi and negative pi, we're gonna end up with two values here that they are identical over the same line here, for this one to be like 2 omega 0, right? So if we connect these points, we're gonna end up with a curve which is gonna be very similar to this case. Then we're gonna have a curve in this case. This curve is commonly known as the dispersion curve of this monoatomic lattice or this material. As you can see, we end up with just one curve. Why we end up with just one curve? Because we have single degree of freedom system. So what does it mean this? It means that depending on how many degrees of freedom do we have in the lattice, we're gonna end up with number of curves. So for example, we would have more curves depending on the number of degrees of freedom that we do have for the lattice itself. We are interested in the dispersion or the vibration of the atom, just one atom, which is atom n. So that's why we end up with only one curve for this atom vibration. So if we try to read, there are lots of things that we can figure out from this dispersion curve for this monoatomic lattice, that basically this curve relates the omega, the frequency, to the wave number. And again, there are so many physical applications that we would need this dispersion curves for. So the key idea here of this demonstration, before we proceed to the diatomic lattice and do the same, the key idea here that in case that we do have a monoatomic lattice and these atoms are moving, again, this atom would be particles, would be molecules, would be grains, would be anything. In terms of mechanics, we do have a monoatomic lattice or arrangement of one line of particles that they do have some interaction between them. This interaction can be represented like a spring. We can mechanically represent this lattice as a mass spring system with a stiff K and mass M. Then we can, from the dynamic equilibrium of this, of one atom, we can end up with an equation of motion, because system with this specification, it is a single degree of freedom system. And again, we are representing these particles as points. So point, it has only one type of degree of freedom that it can move with a displacement u, and we were interested in the vibration of only one atom. So that's why we end up with only one equation of motion, and then we solve this equation of motion to end up with the vibration of this atom up on an incident wave. Make sense? We can do the same, typically the same what we did here for the for a diatomic lattice. A diatomic lattice, it is a little bit different lattice. Like the unit cell of the lattice, it will not include just one atom, but instead it's gonna include two atoms. So that's why it had the name as diatomic. We may have multiple atoms by one unit cell. For example, in the monoatomic lattice, we had in the unit cell, which is the yellow highlighted part, that this part that I highlighted, this would represent like this one here. Here, this yellow part, this would be considered like the unit cell, which it should be repeated. But here the unit cell include only one atom. In some cases, we may have the unit cell that include two atoms. This depends on the material that we are considering or the crystal structure that we are considering. It depends on so many things. So now let us have more advanced level of this model in case that would have a diatomic model. So for this diatomic lattice, which is gonna be like in this way. So, all right. So the one unit cell, only one unit cell will include two atoms. So these two atoms form one unit cell, and there is some interaction between these two atoms. And then we're gonna have another two atoms that form another unit cell, and there should be an interaction between them, and so on. And as we keep going, we do have two atoms. So as you can see, generally the lattice, it is very similar to the monatomic lattice, but for some reason we have to assume that the unit cell is typically like this one. All of this is a unit cell that include two atoms, and there is two springs between them. In the most general case, that this atom would have a mass like M1, and this is another mass as M2. And this spring would be with a stiffness K1, and this spring would be with another stiffness in the general case. So we're gonna have a unit cell, then we are going to repeat this unit cell. It means that we're gonna have here M1, and then we're gonna have here M2, then this should be like M2, and this should be M1. So we're gonna have like M1, M2, M1, M2, and repeat. Here we're gonna have K2, then we should have K1, and then K2, here we should have K1, here K2, and so on. So this is in case that the interaction between the atoms, it is not identical. So in this case, we have to consider the unit cell as diatomic, as already shown here, right? And let us assume that this unit cell is unit cell number N, that this is the unit cell N, for example. So it means that here, for example, we're going to have another unit cell, which it should be N plus 1. And here we're going to have another unit cell, which it should be the N negative 1. Make sense? Then let us assume that the displacement of the two atoms here, even if you remember from the vibration class, these two atoms, they should have two different or two independent displacement. It means that the displacement of mass 1, it is not necessary to be the same as the displacement of M2 because of the spring in the middle. But if we get rid of the spring and we do have some rigid element here, intuitively we're going to end up with the same displacement. So that's why this could be considered as two independent degrees of freedom. So this diatomic lattice model is 2-degree of freedom system. The previous one, the monatomic, it was just single degree of freedom. So let us assume, for example, like U for the mass 1 that belong to unit cell N, and V, this is the displacement of mass 2 that belong to the unit cell N. So for example, what should be the displacement of M1 that belong to the unit cell N plus 1? It should be the UN plus 1. And the displacement of mass 2 that belong to the unit cell N plus 1, it should be Vn plus 1. Here the displacement, it should be the it should be Vn, because this is for mass 2, right? So this should be Vn negative 1, but here the displacement should be Un negative 1, and so on. Make sense? So here we are interested in investigating the vibration of these two atoms that belong to the same unit cell. So that's why this is a 2-degree of freedom system, because we do have two independent unknowns here, or independent variables, which are these two displacements. And again, all of these atoms are, or all of these particles are points that are confined to move in the horizontal direction, in the x direction. There is no vertical movement. So that's why every one of these atoms, it has only one type of degree of freedom as displacement. It can only move parallel to x or in the horizontal direction. And since we do have within one unit cell two different displacements, so the unit cell it should be represented, or the dynamics of one unit cell, it should be represented using two equations of motion as we discussed before. So generally for a diatomic lattice model, it has two different masses in the general case and even two different springs. But let us consider, even if these two masses are identical and these two springs are identical, we can choose a unit cell that confined to atoms, and in this case we're going to have the diatomic lattice. So, and the unit cell is a representative of the whole lattice, and it is repeated everywhere. As we mentioned, the two atoms of the unit cell exhibit two independent degrees of freedom. Therefore, the model is two-degree of freedom system. And therefore, we are expecting to have two equations of motion that describe the dynamic equilibrium of the two atoms that belong to the same unit cell. And this is what we are going to do. So to drive the equation of motion, again, we have to draw the free body diagram of the two masses. So this is the first mass, and this should be the second mass, M2. Make sense? Then we're going to have some forces that should be set up here. Like, for example, this M1 is already connected to two springs, so there are two spring forces. One is related to the K2 and the K1. So in this case, what I'm going to say, for example, let us assume that UN is bigger than Vn. So it means that the pushing is going to be in this direction. So there should be a spring force here, and this is spring force. It should be switched on the other mass. This is going to be like K1, the bigger displacement, negative the smaller displacement, which is the Vn. Then we do have another spring here, assuming that Un is bigger than Vn and negative 1. So this force, it should be in this direction. It will be the K2 times the Un negative Vn negative 1. And the same here, we do have another spring over this mass, another spring which is Q2 over this mass between Vn and Un plus 1. And let us assume that Vn is bigger, means that the pushing in this direction, so the direction of the spring force, it should be K2 Vn negative the Un plus 1. Make sense? And in addition to these spring forces, we do have some inertia force, which is M1 Un double dot, and we do have another inertia force in this direction, which is M2 Vn double dot. Then we are going to apply the dynamic equilibrium for the two masses about the x-axis for mass 1 and mass 2. For mass 1, it will be M1 Un double dot. For mass 2, it will be, the right hand side will be M2 Vn double dot. Let us focus just on the first mass. So we're going to have this term will be negative K2 times Un negative Vn negative 1, and this term will be negative K1 Un negative Vn, and this should equal to the M1 Un double dot. Apply the same for the second equation, or the second mass, which is the sum of forces along x equal the M2 Vn double dot. This is going to give us at the end this equation, which it should be, this term will be positive K1 times Un negative Vn, and this term will be negative K2 times Vn negative Un plus 1, and this should equal to the M2 Vn double dot. And this is going to give us the first equation, and this is going to give us the second equation. These are the two equations of motion that usually describe a general diatomic lattice model. Again, it is a double degree of freedom system. That's why we end up with two equations as already given here. Make sense? Now, if we assumed, let us assume that we do have, for the special case that K1 equals K2 equals K0, for example, or just K. So it means that this equation, these two equations, will have this form. So we can just arrange these two equations. We're gonna end up with this form here. Okay, so this is the first equation, this is the second equation that we already got here, under the condition that we are using two identical springs, and this is the conventional form of the diatomic, this is the classical form of the diatomic lattice model, where again U and V, these are the independent displacements of the two atoms, and since they are independent, it means that they are two independent degrees of freedom. It means that to fully describe the dynamics of this unit cell, it should be described over two equations as we drive it here. Make sense? And these subscripts refer to the UN, N and N negative 1, N plus 1, refer to the unit cell N or N negative 1 or N plus 1. Then again, let us repeat the same procedure to try to solve or to study the vibration of this system. And as you can see, we're going to do typically the same what we did before, but here we have to assume a trial function for both displacements. Here we do have two displacements, not just one, so that's why we do have a trial function for the un, and there is another trial function for the vn functions or displacements as already given here. The common thing between them that omega and q are the same, because this lattice, it should be subjected to the same wave with the same wavelength with the same frequency. So that's why q and omega for the two functions is the same, but the magnitude, it will be definitely different, that we're going to have two different amplitudes for the two functions as given here. Then what next, we basically are going to substitute. I'm gonna drive this expression. I'm gonna show you how we can obtain this expression. So we have to do some substitution here. We are going to plug this term into these two equations. So if we did so, the first equation, it should be, if we did so, the first equation will be the negative m1 will be the negative of negative m1 omega square, because we're going to do time derivative twice. This is going to give us negative omega square times u, and there should be like qn. We agreed that we're going to collect this term. We can rewrite this one as u times qn power n e negative I omega t. The same thing here. This can be written as vqn e I negative I omega t. Make sense? So we're going to have here like qn, then should be the e I negative omega t. Plus the second term, it should be 2k, which is just constant. Un, it should be u qn e I negative I omega t. And the negative k times Vn, it should be V times Qn E negative I omega t, plus the Q Vn negative 1, it should be Q. It should be V as well. It should be V. So this is going to give us here V Qn negative 1 E negative I omega t, as we did above, equals 0. So this is going to give us the first equation. As you can see in the first equation, there are some common terms that can be cancelled, like this exponential term, this exponential term, this exponential term. Also, if we divided all of this equation by qn, we're going to end up with another form of this equation, which is going to be the negative m1 omega square and u times u, and then we're going to divide by qn plus 2k u, we're going to divide by qn, negative k times v, we are going to divide by qn, plus vq negative 1, because we're dividing by qn equals 0. And this is going to give us the 1 dash. This is the new form of the first equation up on the substitution of this trial function un. Let us do the same for the second equation. If we did it here for the second equation, it will be the m1, the first term will be m1 negative m1 v omega square. It will be m1 omega square v times qn e negative I omega t, plus the second term will be 2k vn, so it's going to be 2k v times qn e negative I omega t, and the third term would be negative un plus 1. So it's going to be the negative k times u qn plus the u qn plus 1, and there is e negative I omega t as a common factor equals 0. Then we can cancel all of these exponential terms, all of them together, and then we can divide this equation by qn. So this is going to give us, we're going to end up with m1 omega square v, we're dividing by qn, plus 2k v, we're dividing by qn, negative k times u dividing by qn, plus u times q plus 1 equals 0. And this is going to give us the second equation. Then if we decided to arrange these two equations that we end up with into the matrix form, we're going to end up with a similar form like this one. How? So let us write these two equations in a matrix form. So we're going to have a matrix here times two magnitudes, which are the U and the V, right? The magnitude of the two displacements of the two atoms should equal to the zeros, because the right hand sides of these equations are zeros. So just collect the terms that include the U. So the coefficient of the U will be 2k negative m1 omega square, and the coefficient of V here will be the negative k times 1 plus q negative 1. Make sense? The same thing for the second equation. The coefficient of U will be the negative k times 1 plus q plus 1, while the coefficient of V will be the 2k negative m2. This should be m2 here, because this is here we are talking about the second mass. It should be m2 omega square. Make sense? Then we're gonna end up with this equation. So this is the equation of motion. If you remember in the vibration, this is the equation of motion. And then we can just, the determinant of this matrix should give us the determinant of this matrix should give us the characteristic equation that we can get by the multiplication of this term times this one negative the multiplication of these two terms, right? So but before we do so, let us assume some things here. We can assume, as I'm using here, omega 0. If we assume that m1, let us assume that m1 equals m2 equals m. Like, even we are using, to make it more simple, we are using the same mass. And then let us assume that omega 0, it should be the square root of the k over m, where we are using k over m, the same k and the same mass, identical masses for the two atoms. So if we substituted with this one here, just consider this one, and did the multiplication, you can just divide by divide by m1, which is just m here, right? Divide by m, and divide by m, and divide this term by m, and this should be over m, and over m. So we're gonna end up with 2 omega 0. This term, negative m, will be cancelled with the m omega square, and it will be squared, right? Because here we're gonna have 2 omega 0, negative m will be cancelled, omega square. So we're gonna end up with omega 0 squared negative omega square squared. This is the multiplication of these two terms, negative the multiplication of these two terms. So this is gonna give us omega 0 squared times 1 plus q times 1 plus q negative 1. So this is gonna give us negative the omega 0 squared times 1 plus q negative 1 times 1 plus q positive 1 equals 0. This is the determinant of this matrix 2, and this should give us the characteristic equation. Now let us do the multiplication of these q terms. So we're gonna end up with 1, right, plus q negative 1 plus q positive 1. Positive 1. And then we're gonna have the 1, because this term it should be like q negative 1 times q positive 1, right, which should give us 1. So if we collect this term, just work on over this term here, this is gonna give us 1 plus 1, so this is gonna give us 2, because this one it should be 1, right? So 1 plus 1 gives us 2, and we demonstrated earlier that this q negative 1 plus q1 gives us 2 cosine q, as we did it with the monatomic lattice. So this is going to give us 2 cosine q. So if we plug this here, we're going to end up with this equation that omega 0 squared negative omega squared squared, it should equal to, if we move this one to the other side, it should be equal to the omega 0 squared times the 2 plus 2 cosine q. Make sense? Then we can take the square root of this term. Let us have the square root of this term. So this is going to give us the omega 0 squared negative omega squared equals omega 0 times the square root of 2 plus 2 cosine q. Make sense? Then if you move this one here and move this term here, it seems that I already okay. No, this one it should be like, yeah, this omega 0 square, this should be omega 0 power 4. This should be omega 0 power 4. This term, it should be power 4, and this should be power 4 here. So if we take the square root, this is gonna give us the, yeah, again, this is gonna give us omega 0 square. Then we're gonna move this term and move this term on the other side to end up with omega square equals, moving this one will be omega 0 square as a common factor 1 plus the square root of 2 plus 2 cosine q, which should give us the same equation that we drive it down here, right? Okay, there should be some, yeah, there should be a 2. I forgot this 2, like here we don't have this term, it is 2k over m, so, and here 2k over m, so it should be 2 omega 0 square, not just omega 0. So I forgot 2 here, so there should be 2 in this term here, and as well there should be 2 in this part, like 2 omega 0 square. Also here we're gonna have 2 omega 0 square. Then if you move this omega square and move this one, so we're gonna end up with 2. There should be 2 here. Make sense? So we're gonna end up, now it should be fine. So we're gonna end up with this expression that we already just drive it before into this equation. So this is the equation of motion in the matrix form, and after we did the calculation for the determinant of this matrix, we end up with this equation for omega square equals 0 omega square 0 square 2 plus or minus square root of 2 plus 2 cosine omega, where the plus and minus, and there should be here a plus and minus because we already took here the root. When you apply the root for both sides, there should be plus or minus here. So the plus or minus, and when you move this one to the other side, we're gonna end up with 2 plus or minus the square root of 2 plus 2 cosine q. What do we expect of this equation, which is commonly known as the dispersion relation? This is the dispersion relation, but for a diatomic lattice, for diatomic lattice, that you can just drive this one simply using the same concept of the vibration that you did multiple times before, right? So for this dispersion relation, what do we expect when we try to draw this relation? We are expecting 2 curves, not just 1 curve at the monatomic lattice. Why 2 curves? Because we do have a diatomic lattice, and it is 2 degree of freedom system that had been described by 2 equations of motion, and that's why we are expecting 2 modes of vibration. If you remember the mode of vibration, that if we're gonna look to here, to this lattice, there are 2 possible ways of vibration of these 2 masses, right? So let me draw this one to explain to you the modes of vibration with more representation here. Like, and let us assume that this is the first mass, this should be the first mass, M1, or just M, like we do have one mass M, and there is another mass, which is this one. And there should be some this spring between them, and there is another spring. Forget about these springs, but this mass is already moving with u, n, and this mass is moving with vn. So there are different possibilities here. The first option that you, depending on the incident wave, there is an incident wave going to the mass, to the lattice, so it's gonna produce some vibration in these atoms. So these 2 atoms would vibrate in phase. So this is in phase, is known as in phase vibration. So what does it mean, in phase vibration? This is one shape or one mode of vibration. This is one way of vibration, that these 2 atoms will vibrate in the same direction, that these 2 displacements, un and vn, will be in the same direction, but it is not necessary to be equal. You may have un equal to vn, or un bigger than vn, so you're gonna end up, for example, if un is identical to vn and in the same direction, this spring in the middle will have no vibration. But for example, in the case that Un is bigger than Vn, this spring in the middle will be compressed. In case that Vn is the one that is bigger, this spring in the middle will be stretched. But anyway, since Un and Vn in the same direction, this is known as in-phase vibration. The other option of the vibration of these two atoms, that you're gonna have one atom and there is another atom M here. Let us make it identical, since we do have identical masses. So these are the two atoms, and there is a spring here and there is the other spring. But in this other option, that we may have Vn going in this direction, Un going in this direction, but the Vn somehow, for some reason, is going in the opposite direction. So this is known as out of phase vibration. Out of phase, it means that these two atoms, they're gonna vibrate in two opposite directions. Whatever Un is equal to Vn or different, anyway, the spring in the middle will be compressed, right? And so these are the two different modes. These are the two different ways, nothing more. Since we do have 2 degree of freedom system, we should have 2 equations of motion, we should have 2 frequencies. In addition, we should have, for this system, 2 modes of vibration. So that's why if we try to draw this relation here, this dispersion relation, just draw this dispersion relation, we're gonna end up with a curve which should be typically similar to this case. So this is the dispersion relation here that we are going to draw for the case that Q changes between negative pi to pi, as we did with the monoatomic lattice. So for example, if we plugged Q, let us calculate some values here. For Q equals 0, this term will be 1, so this is going to give us 2 plus 2, this gives 4, so it's going to be the square root of 4. So we're going to end up, this equation will be omega square equals 0, omega 0 square plus times 4, right? Times 2, or it should be times 2 plus or minus 2, right? So that's why we're gonna end up with 2 values of omega. We're gonna end up that in case that this is positive, we're gonna have 4 omega 0 square. In case that the sign in the middle is negative, we're gonna end up with 0. So that's why we do have 2 modes of vibration, 2 natural frequencies. There are 2 possibilities here for the case that Q equals 0. How about the case that the Q equals pi or negative pi? Because they are identical. Because the cosine of any angle the cosine cancels the sine of the angle itself. So the cosine pi is identical to the cosine negative pi, both are negative 1. So we're going to end up with 2 negative 2. It means that this term will be cancelled. So what does it mean? It means that the equation becomes omega square equals omega 0 square times 2. It means that the 2 possibilities, it had been confined into just one possibility or one natural frequency, which is 2 omega 0 and 2 omega 0 for the both curves. So we're gonna end up, if we try to draw this dispersion relation here, like we're gonna have, this is the vertical axis that indicates this vertical axis, and this is the horizontal one that indicates Q, and this is the vertical one that indicates omega, right? And we're gonna have here the 0 omega, and this should be like pi, and we're gonna have here the negative pi. So for the case that omega equals 0, Q equals 0, we got 2 values for omega. One is 0, the other one is 4 omega 0 square. So let us focus on the first mode. This should be the first mode. Usually the first mode is the mode with the lowest natural frequency. So this should be the first mode, and this should be the second mode. This should be the first mode and the second mode. They are identical for the case that pi Q equals pi. So let us focus on the first mode, that it changes from 0 to 2 omega 0 square at pi. So it's gonna be 0. I'm gonna draw the first mode 0. At pi, it should equal to here, like this value is gonna be like 2 omega 0 square. And for the case that negative pi, it should be the same. Right, it should be the same value. So if we decided to draw the first mode, it's gonna be shown in this way, like it's gonna be a curve identical, very similar, not exactly identical, but it is very similar to the curve that we obtained for the dispersion relation for the monoatomic lattice. This is the first mode vibration of this diatomic lattice. How about the second mode? I'm gonna generate or draw this one with a different color in this case. So let us just give a space here up with omega, and let us use a different color. So when Q equal for the second mode, when Q equals 0, it was 4 omega 0 square. This is just 2 omega 0 square, so it's gonna be jump up here like this. Let us assume that this is omega 0 square, it should be higher. Then at Q equals pi and negative pi, it should be coincident with the 2 omega 0 square like the previous mode or the first mode. So we're gonna end up with another curve which is gonna look like in this way. And these 2 points, they should be considered the same. So this curve, this one is the first mode of vibration. This is in terms of vibration concept or keywords. Here we are talking mechanical things, right? And this is the second mode of vibration. This is the second mode of vibration. Very simple. Make sense? From the physics point of view, this first mode of vibration is commonly known as acoustic mode. Is known as the acoustic mode. That's why there is a field of study in physics, especially the vibration of sound application, that we are talking about acoustics all the time. Acoustic, it means it is just a vibration, but vibration that is more oriented to the sound application or wave propagation through this diatomic lattice. So first mode of vibration here, it is commonly known in terms of physics as the acoustic mode of vibration, while the second mode which usually takes place at higher frequency, this is known as the optical mode of vibration. So, or basically we can say that this is like optics. This one is known as optics, or could be named as the optical phonon. And this one would be called acoustic phonon. This is what it is commonly known in physics. Acoustic phonons and phonon, generally it is vibration. Phonon, this is the mechanical description of the vibration of atoms about their equilibrium position within a certain diatomic lattice or a certain lattice model. Like for a single or monoatomic lattice, would have only one curve because we'd have only one mode, which is the acoustic mode, which is the acoustic phonon. So acoustic phonon like it is mechanical vibration. It is light vibration. So generally, phonons in physics, the in-phase vibration in physics is commonly known as acoustic phonons, while the out-phase vibration is commonly known as the optical phonons. Phonons in general, they are mechanical description of the different modes of vibration of atoms when the lattice subjected to some incident waves. So these are the dispersion relation we have investigated, and for example, the optical phonons or optical modes are used a lot for the design of these materials for optical application, while the acoustic phonons are used a lot for the design of sound of material or the implementation of material for sound applications. So all the sound application and optical application use these different types of phonons, and it is used in physics a lot in the design of this material. So what I'd like to demonstrate through these two examples, the first one, which is the monoatomic lattice, and the second one, the diatomic lattice, that you should understand that everything related to the vibration or the movement of the particles inside the material. Like generally, if you do have a material and somehow you are interested in studying the mechanics of the particles of this material, this particle represents something of this material, represent the main building unit. It would be atom, molecule, a grain, if we are talking about a polycrystalline material. So this particle is the representation of the main building unit of this material. If you are interested to study the movement of this particle inside the material, this is known as the particle mechanics. This is from the mechanics point of view. or it would be considered from the physics point of view that you are interested in the dispersion relation of this material, which basically related also to the vibration or the movement of these atoms or molecules inside the material microstructure. So everything is dependent on how these particles are vibrating or moving inside the material microstructure. So that's why in this first part we're already covering these, we demonstrate this movement and the mechanics of the particles. Make sense? The next, we're gonna move to the mechanics of discrete systems of particles. We're gonna make it general. We discussed two cases that you have monoatomic lattice with single degree of freedom in one direction, and the atoms are moving only along X or in one direction. And then we consider the case that we do have a diatomic lattice model that only moves in one direction as well, but we do have 2 degrees of freedom. But how about if we do have a discrete system of particles that moves in space in 3 dimensions? This is a more general model. It is not general that much, but here we're going to consider it based on the concept of the classical mechanics. All right, so and it means that we're gonna drive some equations that would be used for the mechanics of discrete systems of particles. Then from this equation we're gonna see how we can move to the mechanics of the continuum mechanics. So let us move to the mechanics of discrete systems. Talk about the mechanics of particles, but in general. So a general model of a discrete system of particles is the one in which the particle is under interaction, that the particle is already under interactions, but with the surrounding particles. But the key idea here that this interaction, that the interaction is a general 3D field or 3D vector. Like the interaction, we, for example, in the monoatomic lattice, we represented the interaction by a spring. And this spring was linear spring, one-dimensional spring. And when we draw the free body diagram, we see that this mass is already under a spring force, which was K times U negative V, for example, right? And so generally, this is just a force. And this force, it is directional field. It is a vector, but this vector is just in one dimension. But a general form or a general representation of the mechanics of particles that in case that we do have this force, which is the spring force, in case that would have this force as a 3-dimensional vector, not just one-dimensional vector, as we explained in the diatomic or the monoatomic lattice model up. So according to the classical mechanics, as we mentioned many times, that the particle is a mass point and it can only undergo 3 translational motions in the 3 space. So that's why the equations of motion are only 3 equations of motion. And these kinematical degrees of freedom of the particle are generated due to either these degrees of freedom. It means that the movement, what makes the particle move, would be some external applied forces over the system of discrete particles, or some internal particle interaction forces that generate between the particles themselves. And we're going to discuss this with more detail. So for example, the interparticle interactions or the internal interactions that generate between 2 particles, it can be represented as we discussed in the monoatomic and the diatomic lattice, that we can represent this interaction like a spring. So we can have like a spring force. But in the 3-dimensional case, or the general form, that this 3-dimensional, this force, it is not one-dimensional, it should be, this is spring force, it should be a vector. It means that it can be decomposed into 3 components as vector here. So the force field or the interparticle interaction force, it should be a vector field, which can be defined in this form. It is just the spring force, which it should be K times the displacement. But it is not just the displacement, because for example, so to explain this point, let us consider that we do have 2 particles. One particle is M, and there is another particle which is N. And we are interested in the forces that would the particle M act over the particle N due to some intermolecular forces or some interparticle interactions. We said that there would be some interaction that would be generating between these 2 particles. These interactions would be uniform. Like for example, for example, if this one carries a negative charge and this particle has a positive charge, so there should be some interaction between them. It will be attractive force generated due to the difference in the polarity of the two particles, and this would happen, right, in case that we do have a polar material. And in this case, we're going to have interaction. This interaction is due to electrical field. Also, it would be like a magnetic field generated here, or it would be like the gravitational field in case that this mass or this particle is too big in comparison to the other particle. So generally, there are some interactions that would be represented like a spring, as we normally represent these interactions in the simplest form as a spring. It means that there should be some spring force here, and this spring force in the three-dimensional space, it should be a vector force. It is just not one component, it should be a vector. So a vector force, it means that it has three components, one component that should be parallel to x, one component that should be parallel to y, and the other component that should be parallel to the z direction. Make sense? So how we can end up with this spring force? As normal, the spring force, it should be the k times the displacement, right? But this displacement itself, it is a vector, and this one, it should be vector. So what does it mean? It means that this k should be tensor. So there is a type here, this k, it should be tensor. This one, it should be tensor here, right? Tensor, which order of tensor? It should be second order tensor. So for example, in case that this second order tensor, because if you remember from the vector calculus and tensor calculus, in case that if vector, it should be the k, which it should be tensor, dot this displacement generally, whatever it is, just displacement a vector. So if we decided to write this one in the in terms of the elements of this tensor and this vector, so we're gonna say that we do have the kij delta I delta j, which are the tensor form, dot the for example, or uk delta k, right? Then we're gonna end up with kij uk. This is gonna give us the delta I times delta jk, because delta j dot delta k, this gives delta jk. So we're gonna end up that ki j uj, this is gonna give us the force vector, and it should be delta I. Delta I, it means that this is just a vector. So this is the vector force that we're gonna end up. And in case that I is x, we're gonna end up with the x component of this force. In case that I it is y, so this is gonna give us this y component of this force vector. In case that I is z, we're gonna end up with the z component of this force vector. So that's why in the general case, the force that generated between the particles, it is not just one dimensional, it is three-dimensional vector in general. So the general expression of the force, it should be k, which it should be a tensor, second order tensor, that represent the equivalent stiffness of this spring that is set up between these two molecules, and times dot product, it should be dot product times the the difference in the displacements of these two particles, and these displacements are themselves are vectors. So this is gonna give us the interaction that should be generated between these two particles, or in other words, you could consider that this is the force that particle m affecting or acting over particle n, that this is the force that comes from m acting over n, because if you decided to the direction of this force, it should come from m going to n, because it is u negative m, so it should come from u m going to n. So the direction of force, it should be in this direction. Make sense? So this, it means that if we do have a system, let us talk in general, like in general, if we do have a particle like this particle, for example, that is surrounded with so many other particles, so there should be some interaction forces that is going to generate in the three-dimensional space between this particle and all the other particles. In the classical mechanics, we are representing this particle as a point, so that's why it has only one type of degree of freedom, that it can move parallel to x, y, and z. So that's why it has only displacement vector that has three components. This u has three components, one parallel to x, one parallel like ux, uy, uz, three components. And in addition, it is indirect interaction with the neighbor particles, with the nearest particle. Like this one, the distance between this particle and this particle is this value, this edge, but the distance between this particle and this particle is longer. The distance here is bigger than this one, right? This is the hypotenuse of this triangular shape. So it means that this particle, it is not a neighbor. It is not a direct neighbor to this particle. The neighbor, the direct neighbor to this particle is this one, and this one, and this one, and this one, that located along these X and Y or horizontal and vertical directions. But there is no, the particles that located over the diagonal for this case, I'm talking just about this case, all of these are non-neighbors. So that's why there is no interaction between this particle or this particle. The interaction is just between the neighbor, the nearest particles. So this interaction, it is just a force, like a spring force. And this is the general form of this interaction that is going to be generate between two particles, two neighbor particles, is going to be a vector in this form. So for example, if let us talk more general here, like how about if we do have a particle M in, how about if we do have a particle N here, and this particle is surrounded with so many neighbor particles. These are, all of these are, you know, like these are the other particles, but there are a few of them that already actually neighbors. So there should be some interaction between the particle N and just the neighbor particles, like these ones, for example. So it means that in total, how many forces that particle N will be subjecting to, it will be subjected to into one force, like this is going to be like F1, and there should be F2, F3, and F4, and F5. And all of these forces, if we decided to form them using this expression here, all of them will be directed to the particle itself. Like we do have F1 directed in this way, another F4, F2, and F3, and so on. So if I ask you to write the dynamic equilibrium of this particle, the dynamic equilibrium of this particle under the influence of this force, somehow this particle, it will move with a displacement, let us give with a displacement u in this direction, for example. So it's going to move with un, this is the displacement of this particle. So if I ask you to write the dynamic equilibrium of this particle, according to the Newton law, that the sum of forces acting on any object, it should equal to its inertia force, which is the mass times the acceleration, which it should be u double dot n, because this is the displacement. If you differentiate the displacement once with respect to time, gives velocity. If you differentiate it one more time, this gives acceleration. So it means that we do have the mass times the acceleration. This is the Newton's second law. And the sum of forces, how we do have so many forces, it means that we do have the F1 plus the F2 plus the F3 plus the F4 plus whatever, all the forces, just collect all the forces, it should equal to the mass times the acceleration, which is un double dot. Make sense? And you should keep in mind that all of these forces are vectors. Vector. This is gonna give us also the displacement or the acceleration term, it should be vector, where m here stands for the mass of this particle, of the particle. Make sense? This is simply, if I ask you, in case that this is the more general case, that would have a particle located in a system of discrete particles surrounded by other particles, and there should be some interactions here. How about if we are adding more force? Like, for example, how about if there is another force that already, like external force, like there is big external force, F external, for example, already acting over this particle, and there is a vector as well. So this external force will be added to the list of the forces here. So we're going to have like F external vector that should be added to all of these forces acting on this particle according to the Newton's law. Very simple, right? So in general, we can write a general expression of this equation that we're going to say that the sum of all the forces, this is the general expression, that we're already summing the forces that comes from all the particles surrounding the particle n, acting on the particle n, equal the mass times the un. This would also include the external forces as well. Make sense? But there is another thing. If we're gonna consider, how about, for example, if let us consider this drawing. It's going to be much more clear. How about if we do have this particle here, this particle M, and there is another particle N. And as we agreed that there should be some force that comes from M acting over N, right? So, and for some reason, it is not necessary, as I'm presenting here the forces, right? F1 and F2 and F3 and F4. It is not necessary that this force, it could be directly going from M, going directly to N. So for some reason or some cases, we may experience a force that this force that comes from M, it would be directed in this way. That this is the FNM vector, for example. It is not direct, it's not going to the particle directly, but it is the force that comes from M acting over N, but it is not necessary to be directed or going from M to N, right? And let us assume that there should be a distance between these two particles here. Like there is a distance between them, and this distance, it can be decomposed into two components. Like one component is going to be perpendicular to the force here, like there is a vertical or a normal distance to this force. So what do you think? Assume that there is like even this distance, like a rigid body here. So this force that already comes from M acting over N, it will have two effects over the particle N in this case. It will result in some force as a direct effect, as a force, but in the meanwhile it would give a rotation. If we just consider there is like a little bit small pivot here in the middle, assume that in the center of the distance between these two particles. So what's going to happen basically, this force, if this force push in this direction, we're already giving kind of rotation to these two particles, right? It means that the displacement of the particle N, UN itself, it will be a displacement due to two effects. One effect that comes as the direct effect of the force as a force. The second effect that comes of the indirect effect of this force as a moment. So, and let us assume that this vertical distance, like normal distance, like x. So we're gonna say that this force will be force vector, so it will have effect. In addition, it will produce moment. This moment will be the x cross. This is the x, which it should be the normal distance cross, or the x, basically the x, or forget about this one, x, it should be the distance between the two particles. So it should be the x cross the FNM vector. The cross product here gives the normal distance. If you try to cross product this distance between the two particles x, which this distance itself, it is a vector. So this should be vector here in this case. And the force itself, it is vector. So it means that we do have the cross product of two vectors, as we discussed in the vector calculus. This is going to give us another vector. So we're going to end up with a moment, and this moment itself, it is a vector. So it means that this force, in the general case, here we just try to collect the more general case of the interactions between the particles. In the beginning, we discussed like these forces already going to the particle itself, but it is not necessary that these forces going to the particle. It would be directed in any other direction. So in this case, there would be some moment that it should be generating, right? So if in case that this is the direct effect like a force, and in the meanwhile, it's going to have another effect like a moment. Make sense? Which is going to be the x cross product of the force vector itself. So, and that's why, for example, if you remember from the dynamic class, to achieve equilibrium or the dynamic equilibrium of any object, we basically, in case that we don't have moment or there is some possibility for the object to rotate due to the external force, so we used to apply that the sum of forces, it should equal to the mass times the acceleration, which is u double dot. In addition, that we have to apply the sum of moment, it should equal to the rotary inertia, which it could be written as the x cross product of the mass u double dot. It means that this is the linear inertia. If you multiply cross product by a displacement, this gives inertia moment. This is the inertia moment. Make sense? So generally we're gonna say that the equilibrium, it is not just over the force. There should be equilibrium also over the moment that would be produced because of this force about the particle n. So that's why in general, in case that we do have a particle that is located within a system of particles, in the most general case, there should be some interactions. All of these interactions are forces, but these forces, they do have two effects. One is a direct effect as just direct force. The second one, it would be in the form of a moment that acting over this particle. But the moment here, there is a key point, that the moment that comes from the force, it gives rotation to the particle. No, the particle is not rotating. Remember that the particle is still a point. But if you just assume that there is like a stick, as I give you this very simple model to understand the effect of this, the moment of this force. Assume that these two particles connected somehow by a stick. This stick has a stiffness, and this is the spring stiffness that we're already talking about, right? So because of the force, these two particles will start to rotate. So the particle n is still moving, but its displacement will depend on the direct effect of the force, adjust the force, because the force pushes something. But in the meanwhile, this force is not pushing. It gives rotation to the system, gives rotation to these two particles. This rotation as well will affect the generalized displacement of this particle n. Make sense? So that's why the dynamic equilibrium of the particle, it do depend on two quantities. It depends on the force as a direct effect in addition to the moment due to this force as indirect effect of the same force. Make sense? So that's why these two equations, these are the equations that form the dynamic equilibrium in general for any particle belong to a system of particle. Like under the influence of these interactions, or the interaction forces that generate between the particle and all the neighbor particles, all of these forces, the dynamic equilibrium of a particle n is conditional by the following balance equation, that the sum of forces of interaction between the particle n and another particle m, it should be the mass of the particle n times the displacement of the particle n itself, double dot. Double dot indicate that this should be the acceleration. This is the inertia, this is the linear, or this is the force inertia. This is the force inertia of the particle, but this is the moment inertia of the particle. So we already have this force, this is the force, and this is the inertia term, and this is the sum force. Here we're already summing over m, that it changed from 1 to nm. What is nm? This should be the number of neighbors particle to the particle n. That this equation indicates that we're already collecting all possible forces that comes from the neighbors. Each one of these neighbors will be considered like m. And for example, let us give numbers to these neighbors. So we're gonna have here, it is crazy using these things anyway. So we're gonna have here like 1, and there should be 2, should be 3, and 4, 5, 6 neighbors, for example. So in the beginning, n in this equation, m will be 1. So I'm getting the force that comes from particle 1 acting over n, plus, because we already summing, in case that m equals 2, so I'm getting that fn2. It means that this is the force that comes from particle 2 acting on particle n. Then in case that m is 3, so it's gonna be fn3, and so on. So we're already collecting all the forces. It means that the expanded form of this force term will be fn1 plus fn2 plus fn3, and so on, fn4, and so on, depending on how many neighbors to the particle n. Where the fn1, this is the force that comes from the particle 1 that acting over particle n. This is the force from particle 2, this is the force from particle 3, this is the force of interaction between n and particle 4, and so on, depending on how many neighbors. In addition, each one of these forces will have a moment. The moment, it will be x cross product of the force field itself. What is this x? This is the position, this is like a distance between this particle and the other particles, like the distance between the particle and particle 1, the distance between the particle and particle 2, and so on. And this should give us the x cross the mu double dot, which it should be the moment inertia. So these are the two equations that we already have to achieve the equilibrium over the force and over the moment in case that we do have a general system of particle. These are the dynamical equation of motion, or these are the equations of motion or the equilibrium equation for a discrete system of a general model of a discrete system of particles. But you should understand something here, that all of these particles still represented as points in the classical mechanics. And that's why we do have the equations of motion are dependent on the displacement u. So the question is, how many equations of motions do we have here? If we decided to collect this equation, for example, if I ask you to write this equation will be decomposed into three equations because this is a vector, it has three components. This one is a vector, it has also three components. So if I decided to write this equation, these equations in the general form, in a more general form, an expanded form here. As for the first equation, I'm gonna just get rid of the nm and the n here. That's in general, as I wrote the equation, the first equation should be that the sum of forces as force vector, it should equal to the mass times the u double dot vector, right? Each one of these vectors has three components, so it can be decomposed into three equations here. It can be decomposed into three equations. If I ask you to write this equation in terms of the components of these force vectors, so we can write this one as the sum of Fi delta I. Agree? I'm just using the component of the force vector equal the mass. Here we do have u vector double dot, so it should be like u double dot as component I delta I. Why I'm using that? Because I have moved to another term. This is one term, and here I move to the other term, so I have to use the same index, the same order of the index that I used before, right? So what does it mean? It means that in case that I is x, we're gonna have here delta x, and we're gonna have delta x. It means that we're gonna have one equation that states that the sum of forces along x, delta x, it should equal to the mu x double dot delta x. And this is what we already used to use for the dynamic class, for example. It was mentioned for you that when we apply the Newtonian's method for the dynamics of particles, for example, that the sum of forces, you're going to collect the forces parallel to x equal to the mass times the acceleration along x. The acceleration part, it has three components. The same thing, the sum of forces along y, it should equal to along y delta y, it should equal to the mass uy double dot delta y. This is the same thing for the sum of forces along z, delta z equal the mass uz double dot delta z. Make sense? So that's why we're going to end up with three equations that describe the dynamics of this particle. But how about these other three equations of the moments? Because the moment itself is going to give us another three equations, right? We mentioned before that in case that you do have a particle that belong to a discrete system, and this particle is a point, it has only 3 degrees of freedom. It has only 3 displacements, one along x, one along y, one along z, right? Make sense? So it means that the dynamical equilibrium of this particle, it should only dependent on 3 equations of motion, should be described by only 3 equations of motion. So we already got 3. How about the other 3 equations of motion? These 3 equations of motion, these other 3 equations of motion describe not the motion of the particle itself, it describes the rigid rotation of these 2 particles together. So you could say that these other 3 equations, they are not just related to the particle n, but they are related to the particle and the other surrounding particle, because we're already collecting here. Like this moment, the moment that comes from the force, This gives rigid rotation. This gives rotation not just for n, it gives rotation as well for m. So this moment term, it belongs to both, to n and m. But the equation that just belong to n are only three equations, which are the force component, right? Or the force equation, the three equations. But these three equations of the moment, these are the equations that belong to the whole system of particles. You got my point? So that's why the dynamic here, this equation, this is the dynamic equilibrium of just single particle, and this makes sense that we already have just three equations because we have 3 degrees of freedom for one single particle. But this equation is the dynamic equilibrium of the whole system of particles, of all the particles together, like this system already rigidly rotating in one direction because of the moment of the forces that generate between these particles themselves. Make sense? It would be somehow unclear to you at the moment, but anyway, the overall dynamical equilibrium of the whole continuum is described by these 6 equations. Then when we move to the continuum mechanics, these 3 equations will be combined together somehow into just 3 equations. But you should understand that the dynamical equilibrium of any particle, individual particle inside the system of discrete particle is just, if you just apply the dynamic equilibrium to any particle, it will be described only by 3 equations which are related to the force acting on this particle. But in addition, these forces will produce some moment effect. This moment effect would result in some rotations or moments for this system of particle, and that's why we may have this system of particle would rigidly move or rotate because of these moments due to these force vectors. So that's why we're already having here the other 3 equations of the moment. How about if we decided to write these 3 equations in the vector and the component form? These equations are the sum of x, which is just a vector, position vector, cross the force vector. This is the moment. It should equal to the x cross the moment u double dot vector, right? So let us do the cross product. This is gonna give us the xi delta I cross the fj delta j. We're still working on the same term equals. Then now we're gonna move to the next term, to the other term. So we have to use the same indices that we used in the first term. So we started with the I index. So I'm gonna have here the xi delta I cross the m, just a constant, but this u, it is a vector, so it's gonna be like uj double dot delta j. Then if we did the cross product over the unit vectors, we're gonna end up with xi fj xi delta j. This gives us the epsilon I j k delta k. If you remember, this equals the xi uj double dot delta I cross j. This gives up epsilon I j k delta k as well. Make sense? So this is gonna give us the equation of the moment, and that's why generally we're gonna say that we can even cancel this one with this one, or just consider these terms will not be cancelled, but it will be considered like a common factor. So we're gonna end up with this expression like xi times fj equal the xi uj double dot, which is gonna give us the commonly known moment, because x, which is distance times force, this gives moment, and this is there is a mass here, I forgot the mass, so there is an m here. This also inertia force times x, this also gives the moment, another moment, which is the inertia moment. And this is this is what we used to write in the dynamic lattice, that the sum of moment, it should equal to the I theta double dot. For example, if you decided to get rid of the linear acceleration and use the angular acceleration, which is theta double dot. Make sense? So what I have formed here, basically we discussed the up to here the general mechanics of particles, and we explain these 2 equations. These 2 equations are very common for the general mechanics of particles, but we explain them deeply kind of to understand what are these forces. the key idea here that you should understand that these forces that I'm presenting here, F and X cross F, this force F, this is the interparticle forces. These are the forces that is going to generate between two particles. But you should understand, in addition to these two particles, we would have some external force here. In addition to this interparticle forces, Fm and M, we may have some external force. So in this case, you're gonna have an extra term that should be added here, plus F external, and it's gonna be a vector force as well. Make sense? But generally, the common thing of representing this equation that we skip the external force for this case. All right. So I'm gonna stop here for this part for today's lecture. The next meeting, I'm gonna show you how we can, starting from these two equations of the mechanics of particles, how we can form the equations that we're gonna use through this course for the continuum mechanics. And then we're gonna discuss, in the meanwhile, we're gonna discuss what does it mean deformation, what does it mean strain and stresses. I'm pretty sure that these keywords that you have an idea about them before in the mechanics class, but we're gonna discuss them in relation to the mechanics of particles. So again, as a quick summary of today's lecture, the main idea of today's lecture is just to understand what does it mean mechanics. Mechanics simply is to study the behavior of material, and in this class we are interested in studying the behavior of solid objects, and not any type of solid object. This solid object should be made of a material. This material should be linear elastic material, and we are going to discuss this with more detail in other lectures. But since we are interested in investigating the mechanics of this solid object, we have to use a mechanics method. We do have in general two main types of mechanics, which are the classical and the quantum mechanics. Quantum is very advanced mechanics, and it is used a lot by the physical guys, the guys who are really interested in physics. But the classical mechanics, and this is the type of mechanics that all the courses that you studied so far in the undergraduate and even in the graduate course are based up on or depend on or has been established based on the classical mechanics. The classical mechanics based on three main assumptions, or depend on three main assumptions. The first one, that the material is homogeneous. The second one, that the material is a composition of an infinite number of particles. And the third one, that each one of these particles is a point. If we decided to do changes to these assumptions, we're gonna end up with a more advanced classical mechanics, more advanced mechanics, like for example the micropolar mechanics, that we're considering the particle as a volume element that can rotate. So, but in the classical mechanics, we do have the particle is just a point that can only move. Point, it means that it has only one type of degree of freedom, that it can move along X, Y, and Z. So this in total 3 degrees of freedom of the particle. So that's why we are expecting that the equilibrium, whatever it is, a static equilibrium or dynamic equilibrium of any continuum, it should be represented by only 3 equations of motion. And this is what we are going to drive the next meeting. But then we discussed the relation between the mechanics or the behavior of the material in relation to the particles movement inside the material. And we said that this particle that located inside the material, this particle represents the main building unit of the material. And we give an example of a polycrystalline material that this particle would represent the grains. And if we go deeply inside the material microstructure, we will realize that this microstructure is in general heterogeneous. But in case that we are interested in the overall behavior of the material, so we have to deal with this material, or that is fine to assume that this material is a homogeneous, and the properties of the grain is a representative thing to all the properties of the entire material. And in this case, according to the mechanics, that is fine to you, that assume that this grain is the particle in the context of the classical mechanics. Then we discussed and we explained that everything is related to how these particles are moving inside the material. Like, in order to understand the deformation, the strain, or the behavior or the mechanics of this material, and this is what we're going to discuss through the rest of the course, All of these mechanics of this material are related to how these particles already interacting together, how they are moving inside the material. So that's why in today's lecture we focus somehow on the mechanics of particles. Mechanics of particles, it means that we studied how these particles are vibrating, and we considered three different cases. In case that would have a monoatomic lattice, that in case that would have an incident wave over a monoatomic lattice, these atoms inside the material, which would be the particles, will vibrate. Then we drive the relation between the frequency of the incident wave in addition to the wavelengths as one of the applications that is used a lot in physics for the acoustic application, for example. Then we consider more advanced model, which is the diatomic lattice. And for the diatomic lattice, there is a 2-degree of freedom system. So that's why we end up with two equations of motion. And that's why we end up with two modes of vibration of these two particles. And we end up with two curves in the dispersion diagram of the diatomic lattice. Then we move to a general model of the particle, that generally the particle is a point that can move along x, y, and z. So it should be described by three equations of motion. And this general model depended on, which is already shown here in this equation, it depended on the interactions between two particles, or the particle and all the other surrounding particle of within, in case that would have a particle located inside a discrete system of particle. And we said that this equilibrium of the entire system, here this is the equilibrium of the system. And especially the first equation, this is the equilibrium of the particle itself at any point or at any particle. But in the meanwhile, we have to consider this equilibrium of the particle in relation to the equilibrium of the overall, the entire system of particles. So that's why we do have other three equations of the moment, which describe how this system of particles is going to deform. If we're gonna look to this system of particle like a bulk thing, how this system of particle is going to rotate or deform up on the forces inside or that generate between the particles themselves due to the moments. So this is like the direct effect, and this is like the indirect effect of these interaction forces. The next meeting, we're gonna start from these two equations, moving to the continuum mechanics and how we can drive the equations of the continuum mechanics. The difference between the particle mechanics or the continuum mechanics. In continuum mechanics, we don't care about the movement of the particle. We're just interested in the entire material deformation. But you should understand that this deformation and the equation that we every day use as mechanical engineer for the continuum mechanics, these equations had been derived from these two equations of the mechanics of particle. Like for example, the classical mechanics can be dated back to Newton. And or you could say that the first guy who already started to deeply establish this mechanic that we're already using these days is Timoshenko. This guy, when he discussed the classical mechanics, he started from these two equations, from the mechanics of particle, and how from this mechanics of particle we end up with the equations that we basically gonna use through this course in terms of stresses and the strain. So what is the relation of the stress and the strain to this equation and the movement of the particle? This is what we are going to discuss the next meeting. All right, so that's it for today's lecture, and thank you, and see you in another video.